feature preprocessing or normalization. Since each feature is processed independently and the splitting of the data doesn't depend on the absolute scale of the feature, the decision algorithm can operate on the original training data pretty much as is. So decision trees tend to work well with datasets that have a mixture of feature types, binary, categorical, or continuous, and with features that are on very different scales. One drawback of decision trees is that despite the use of pruning, they can still overfit on all or parts of the data and may not achieve the best generalization performance compared to other methods. One way to overcome that problem is to create what's called an ensemble of decision trees, which combines multiple decision trees to make a prediction. And we'll look at ensembles of decision trees in a following lecture. So to recap, scikit-learn enables you to control the model complexity of your decision trees with three key parameters. First, max depth controls the maximum depth, or the number of split points the decision can have, and is probably the most common parameter used to reduce tree complexity and thus reduce overfitting. The min samples leaf parameter is the threshold that controls what the minimum number of data instances has to be in a leaf to avoid splitting it further. This setting also reduces tree complexity. Finally, max leaf nodes limits the total number of nodes that are leaves of the tree. In effect, setting this parameter will indirectly influence the other two parameters and vice versa. So in practice, adjusting only one of these three is typically enough to control most overfitting. Although even with the most optimized parameter settings, individual decision trees will still tend to overfit. In this video, I'm going to talk about what to do when you have categorical values for features or categorical values for labels. So a lot of the introductory machine learning examples that you might have seen assume that all the features are numeric, and it's a very common situation, though, to have features that are a category of something or a mixture of categorical and numerical features. So we're going to discuss in this video how to handle that particular situation. Okay, so let's take a specific example of what might be a categorical variable that you might see in a particular problem. Let's say we are looking at color. So there's a color feature in your data set, and the color can be one of several possible values. It can be red, yellow, green. It can be 30 different values depending on your application. But in general, the idea is that it's a category. So the category is part of a set of possible values. It's not a numerical value. And many predictors can't take a categorical input like this directly. So, for example, you can't take your color feature with its red, yellow, and green values and use it directly with, linear regression or logistic regression or support vector machines. Some methods can take categorical variables directly, like decision trees and decision tree-based predictors. But you may be faced with a situation where you have to figure out what you need to do to use categorical variables with a prediction method that can't deal with them directly. And by the way, some of these categories are encoded as numbers. Even though they're not numerical data, the categories might get mapped to numbers. So red might equal 1, yellow might equal 2, for example. So even if a column in your data set looks like it's a numerical feature, it may actually be a category feature encoded using numbers. So just be aware of that. So one very widely used solution to deal with categorical variables is called one-hot encoding. And what that does is it takes a single categorical value and turns it into a vector of binary values. The way the encoding works is you look at your categorical feature and you make a list of all the possible values that it could take. So in this example, I've pretended that there are only 3 possible color values, red, yellow, and green. So to get the one-hot encoding of the value red, we simply go through all the possible categories and we store 1 in the column that represents red and 0 for all the other categories. So in the one-hot encoding scenario. It's called a one-hot encoding because exactly one column is a 1, and that's the selected category, and the rest of the columns are 0. Let's take another example. Let's say we want to encode the value green for this row, and that's the 4th row. So you can see that in the one-hot encoding version of green, we have a 0 for red, a 0 for yellow, and a 1 for green. So very simple idea, and it's very widely used in statistics. For example, it's called a dummy encoding or a 1 of k encoding or an indicator variable. So that's how you convert categorical values into a vector of 0, 1 values that something like linear regression can actually handle now. Transforming categorical values into one-hot encodings is really easy in Python, whether you use pandas or scikit-learn. In pandas, we have this function called getDummies. And again, it's named that because one-hot encodings are called dummy variables in statistics. So getDummies can convert these categorical variables to dummy indicator variables. And you can see in this example, we created a list of values, A, B, C, A. And when we ask pandas to create the one-hot encoding for each of these, what it does first is it goes through and makes a list of all the possible values, so A, B, and C. And then for each of the entries, it will go through and mark, for the entry A, it will make A equals 1, and then set the rest to 0, and so forth. So super easy to do in pandas. And in scikit-learn, it's also very easy. Now, there are two cases in scikit-learn to think about. One of them is if your categorical variable is a feature. In other words, it's in the X matrix. In that case, you would use sklearn preprocessing one-hot encoder to create the one-hot encoding vectors for each row for that feature. And you do that using the fit method, which will go through and look to find what are all the unique values in that feature column. And then once the one-hot encoder has been fit and has found all the possible unique values in that feature column, then you call transform to actually create the one-hot encoding vectors for that feature column. And those one-hot encoding vectors, by the way, by default are sparse. So this method produces a sparse matrix by default. You can change that if you want. You can set sparse equal to false. But by default, it's a sparse implementation. The second case in scikit-learn is where the thing that you're predicting, the label, is a categorical variable. So it might be that you want to convert a multi-class label, like suppose you're trying to predict a color. You might want to predict a binary label, so convert that multi-class problem into a series of binary problems. And to do that, you use label binarizer as the class that you apply that to. So it's similar to one-hot encoder in the way that you fit and transform. By default, in this case, actually, just a detail you should be aware of is that by default, that it actually produces a dense matrix in the current implementation of scikit-learn. So you can also, of course, turn that off and select sparse output if you need a sparse set of binary labels. But those are the two cases in scikit-learn where you want to use one-hot encoding, either as a feature or as a label. So here's a coding example that shows how fit and transform are used with the one-hot encoder object. So as usual in scikit-learn, the first step is to create the object. In this case, I'm also passing it the handle unknown option. And I'll talk about what that does in a minute. But right now, let's assume that we have some initial data which consists of 3 rows and 2 columns. So the first column is either male or female, and the second column is an integer, 1, 3, or 2. And when we call the fit method, scikit-learn's one-hot encoder object will analyze that, and it will find the unique values in the first column and the unique values in the second column. So the unique values in the first column would be female or male, and the unique values in the second column would be 1, 2, or 3. And we can see that when we look at the categories underscore variable that is set as a result of calling the fit method, we ask it, okay, what categories did you find in our data that we use for fit? And scikit-learn returns that in the first column, it found female and male as the categories. And in the second column, it found unique values of 1, 2, and 3. Now with this knowledge about the unique values in each category, we can do a transform, and we can ask scikit-learn to create a one-hot encoding vector for the first column, followed by the one-hot encoding vector for the second column. So if you have two successive columns that are categorical values, and you ask scikit-learn to do the transform, it will transform the first value into a one-hot encoding, and then concatenate the one-hot encoding vector for the second value. So let's ask it to transform a new little table which has female and the number 1 in the first row, and male and number 4 in the second row. And let's look at what the output is. So the one-hot encoding, so first it will create the one-hot encoding for female. And you'll notice that the categories that it found originally were female and male. So the one-hot, there are only two possible columns in the one-hot encoding, the female column and the male column. And you'll see that because we have the categorical value of female, it correctly set the female column to 1 and the male column to 0. And you can see for the second row in this mini data set that male got mapped to the one-hot encoding vector of 0, 1. Okay, so it's setting the male category to 1 in the second column. And you can see what it did for the one-hot encoding of the numerical column. So it's treating the numerical column here as if it were a set of numbered classes. And when the second column's value is 1, that gets converted to a one-hot encoding corresponding to this array. So it should create a one-hot encoding vector of 1, 0, 0. And you can see indeed it does. But the second example is an interesting one. It's asking it to create a one-hot encoding vector for a class, or an integer representing a class it's never seen before. You can see that there's no 4 in the set of unique values that it found for those numbers. So this is where the handle unknown setting comes in. So if you set handle unknown to ignore, what it will do is when it sees the value 4 and it tries to create a one-hot encoding for a value that it never saw during the fit method, it will simply create, it'll put a 0. It'll put a 0 in that entry. Okay, so what it did here is it converted the number 4 to a one-hot encoding vector that actually didn't have a 1, so it was all zeros. And that's what happens if you see a class in your test set, for example, that was never seen during training. Using the handle unknown option of ignore, it will create the one-hot encoding vector that's all zeros. The other option for the handle unknown setting, you could also specify handle unknown equals error. And if you do that, then instead of silently creating an all zeros vector for an unknown class value, an unknown category value, it will actually create an error in the code, throw an error in the code, and halt the code. So, but that's the basic operation of one-hot encoder. So finally, here's some rules to make sure that you apply this one-hot encoding step properly. First, like many other types of transformations in scikit-learn, you always split the training and test sets first before fitting the one-hot encoder object. You fit the one-hot encoder object using the training data. You don't pass in the entire data set, including the test set. You must only do it after you split so that the one-hot encoder doesn't get any knowledge of what is in the test set. And then once you fit the one-hot encoder using the training data, you can use the transform function to apply this same one-hot encoder you just fit to both the training data and the test data. So you need to make sure you use the same one-hot encoder for training and test, and you need to make sure that you've only trained it using the training data. And that makes sure that dummy variables match across the training and test data and that all categories are represented. So a question that comes up is what happens if the test set has extra categories we didn't see during training? And this corresponds to the case I just showed you of where we're asked to create a one-hot encoder for the number 4 when the data that was used to fit the one-hot encoder only had values 1 to 3. So you have two options in that case. One of them is you can create a special other category to map any extra categories in the test set to other. Or you can ignore them and allow an all-zero one-hot vector for that particular category, for that item in the test set. When we began working with supervised machine learning methods, we evaluated a classifier's performance using its accuracy. Accuracy, as you might recall, is the fraction of samples that were classified correctly. That is, where the classifier's predicted label matched the correct or true label. We also evaluated a regression model's performance using the default R-squared metric. In this module, you'll learn why measures like accuracy, which are simple and easy to understand, also have drawbacks in that they don't give a complete enough picture of a supervised learning model's performance and may not be the right metric for measuring success in your application. So we're going to cover several additional evaluation metrics beyond accuracy. We'll see how they're defined, what the motivation is for using them, and how to use them in scikit-learn to get a better picture of how well a supervised model is doing on a given data set. You'll also learn about how to choose the right evaluation metrics for your application that can help you select the best model or find the optimal parameters. So let's return for a moment to this workflow diagram that we introduced earlier in the course. You see that evaluation is a key part of this development cycle in applied machine learning. Once a model is trained, the evaluation step provides critical feedback on the trained model's performance characteristics, particularly those that might be important for your application. The results of the evaluation step, for example, might help you understand which data instances are being classified or predicted incorrectly, which might in turn suggest better features or a different kernel function or other refinements to your learning model in the feature and model refinement phase. As we discussed earlier, the objective function that's optimized during the training phase may be a different, what's called a surrogate metric, that's easier to use in practice for optimization purposes than what's used for the evaluation metric. For example, a commercial search engine might use a ranking algorithm that is trained to recommend relevant web pages that best match a query, in other words, trying to predict a relevant label for a page. And that might be the objective in the training phase, but there are many evaluation methods in the evaluation phase that could be applied to measure aspects of that search engine's performance using that ranking algorithm that are important to the search company's business, for example, such as how many unique users the system sees per day, or how long a typical user search session is, and so on. So the evaluation measures are the ones that in the end are used to select between different trained models or settings. Actually, commercial search applications typically use a scorecard of multiple evaluation metrics to make important business decisions or development decisions about what models are chosen for use. So it's very important to choose evaluation methods that match the goal of your application. For predicting the correct digit from a handwritten image, let's say, where each digit is equally likely, then accuracy may be a sufficient metric. However, there are other possible aspects of evaluation and model performance that are beyond average accuracy that may be critical to measure. For example, in a health application that uses a classifier to detect tumors in a medical image, we may want the classifier to err on the side of caution and flag anything that even has a small chance of being cancerous, even if it means sometimes incorrectly classifying healthy tissue as diseased. In this case, the classifier evaluation method would try to reduce what are called false negative predictions. We'll look at this in more detail shortly. More generally, your application goal might be based on very different metrics such as user satisfaction, amount of revenue to your page, or increase in patient survival rates. So in the end, you'll be selecting the model or parameter settings that optimize those end evaluation metrics that are important to your goal. So in this module, we'll be focusing first on the widely used case of evaluating binary classification. And then we'll look at evaluation for the more general case of multi-class evaluation, as well as regression. Before we start defining and using some evaluation metrics for binary classification, let's start by looking at an example of why just looking at accuracy may not be enough to gain a good picture of what a classifier is doing. And it'll also show us how knowing more about the types of errors a learning algorithm makes can help us get a better picture of a model's predictive performance. First, let's consider the case where we have a binary classification task where there are a lot of instances labeled with the negative class, but only a few instances that belong to the positive class. For example, we might see this scenario in online search or recommender systems, where the system has to predict whether or not to display an advertisement or product suggestion, or show a query suggestion or item on a page that's likely to be relevant given a user's query and what they clicked on in the past, and so on. So those would be the positive examples. But of course, there are many, many irrelevant items that are in the negative class that don't make sense to show a user. And so this is called an imbalanced class scenario. Another example might be data sets of credit card transactions, where the vast majority of transactions are classified as normal and not fraud, with a small minority of transactions that could be classified as fraudulent. These situations, which also apply to multi-class classification problems, involve data sets that have imbalanced classes. Imbalanced classes are very common in machine learning scenarios, so it's important to understand how to work with them. In particular, let's assume that we have an e-commerce application where for every 1,000 randomly sampled product items, one of them is relevant to a user's need and the other 999 are not relevant. So recall that accuracy computed over a set of instances is just the number of instances where the classifier's label prediction was correct divided by the total number of instances. Let's suppose you develop a classifier for predicting relevant e-commerce items. And after you finish the development, you measure its accuracy on a test set to be 99.9%. At first, that might seem to be amazingly good, right? That's incredibly close to perfect. But let's compare that to a dummy classifier that always just predicts the most likely class, namely the not relevant class. In other words, no matter what the actual instance is, the dummy classifier will always predict that an item is not relevant. So if we have a test set that has 1,000 items, on average, 999 of them will be not relevant anyway. So our dummy classifier will correctly predict the not relevant label for all of those 999 items. And so the accuracy of the dummy classifier is also going to be 99.9%. So in reality, our own classifier's performance isn't impressive at all. It's no better than just always predicting the majority class without even looking at the data. Let's take a look at another example of classification with imbalanced classes on a real data set using our notebook. I'll start here using the digits data set, which has images of handwritten digits labeled with 10 classes, representing the digits 0 through 9. As we can see by loading the data set and then computing the count of instances in each class using NumPy's bin count method, there are roughly the same number of instances in each class, so this data set has balanced classes. However, with this digits data set, now what we're going to do is create a new data set with two imbalanced classes by labeling all digits that are not the digit 1 as the negative class with label 0, and digits that are 1 as the positive class, label 1. So what I've done here is dump the first few entries from the original labels along with the new binary labels so you can see the imbalance visually. Now when we use bin count, we can see that there are about 1,600 negative examples, but only 182 positive examples. So indeed, we have a data set that is class imbalanced, or as expected, almost exactly a 9-to-1 ratio of negative to positive examples. Now let's create a train test partition on this imbalanced set, and then train a support vector machine classifier with these binary labels using the radial basis function as a kernel. We get the accuracy using the score method, and we can see this is just over 90%. Again, at first glance, 90% accuracy for a classifier seems pretty good. However, now let's create a dummy classifier that correctly reflects the class imbalance to see if 90% really is that impressive. scikit-learn makes it easy to create a dummy classifier just by using the dummy classifier class as shown here. Dummy classifiers, again, are called that because they don't even look at the data to make a prediction. They simply use the strategy or rule of thumb that you instruct them to use when creating them. In fact, when you create the classifier, you set the strategy argument to tell it what rule of thumb to use to make its predictions. So here we set this to the most frequent strategy to predict the most frequent class. The dummy classifier here is used just like a regular classifier. So to prepare it for prediction, we call the fit method on the xtrain and ytrain variables that hold the training set instances and labels. Now, this dummy classifier won't actually be looking at the individual data instances in those variables, but it does use the ytrain variable to determine which class in the training data is most frequent. Finally, just like a regular classifier, we can call the predict method to make predictions on the test set. This example shows the output of the dummy classifier's predictions, and as promised, you can see it's always predicting 0, or the negative class, for every instance in the test set. Now we can call the usual score method to get the accuracy of the dummy classifier's constant negative prediction. And we can see it's also about 90%, the same as our earlier support vector machine classifier with radial basis function kernel. So that support vector classifier was actually performing only very slightly better than the dummy classifier. The dummy classifier provides what is called a null accuracy baseline. That is, the accuracy that can be achieved by always picking the most frequent class. You should not use a dummy classifier for real classification problems, but it does provide a useful sanity check and point of comparison. There are other types of dummy classifiers that provide null baselines corresponding to other choices of the strategy parameter, as shown here. Most frequent is the strategy we've just seen that always predicts the most frequent label. The stratified strategy, unlike the constant most frequent prediction, is a random prediction that's based on the class distributions. For example, if the positive class occurs 90% of the time in the training set, then the stratified dummy classifier will output the positive class label with 90% probability. Otherwise, it will output the negative class label. This can help ensure that metrics that rely on having counts of both positive and negative class prediction outcomes can be computed. The uniform strategy is another random prediction method that will generate class predictions uniformly at random. That is, all classes have an equal chance of being output, as opposed to being weighted by their frequency in the training set. This strategy may be useful in gaining an accurate estimate of what are the most common types of prediction errors for each class. Finally, the constant strategy can be useful when computing some metrics like F-score, which we will cover in a few minutes. Well, why is that? Well, when we have a binary classification task where the most frequent class is the negative class, it turns out that using the most frequent strategy will never predict the positive class and will never be able to count the number of positive instances that are correctly predicted. And so the overall count of such positive correct predictions will be 0. So this in turn, as you'll see in a few minutes, will cause some important metrics like F-score to always be 0. So using the constant strategy, we can force a dummy classifier to always predict the positive class, even if it's the minority class in a set of classes. and this will lead to more meaningful computation of F-score. So what does it mean if we discover that our classifier has close to the dummy classifier's performance? Well, typically it means that the features in our model may be ineffective or erroneously computed or missing for some reason. It could also be caused by a poor choice of kernel or hyperparameters in the model. For example, if we change the support vector classifier's kernel parameter to linear from RBF and recompute the accuracy on this retrained classifier, we see that this leads to much better performance of almost 98% compared to the most frequent class baseline of 90%. Finally, if you have accuracy that is close to that of a dummy classifier, it could be because there is indeed a large class imbalance, and the accuracy gains produced by the classifier on the test set simply apply to too few examples to produce a significant gain. In general, for imbalanced classification problems, you should use metrics other than accuracy. We'll look at one shortly called AUC, which is short for area under the curve. Dummy regressors, as you might guess, are the counterpart to dummy classifiers for regression, and they serve a similar role as a null outcome baseline and sanity check for regression models. Since regression models have continuous valued prediction outputs, the strategy parameter for dummy regressors gives you a choice of function that you can apply to the distribution of target values found in the training set. You can ask for the mean or median value of the training set targets, the value corresponding to the quantile that you provide, or a custom constant value. Now let's look more carefully at the different types of outcomes we might see using a binary classifier. This will give us some insight into why using just accuracy doesn't give a complete picture of the classifier's performance, and will motivate our definition and exploration of additional evaluation metrics. With a positive and negative class, there are 4 possible outcomes that we can break into 2 cases corresponding to the first and second row of this matrix. If the true label for an instance is negative, the classifier can predict either negative, which is correct and called a true negative, or it can erroneously predict positive, which is an error and called a false positive. If the true label for an instance is positive, the classifier can predict either negative, which is an error and called a false negative, or it can predict positive, which is correct, and that's called a true positive. So maybe a quick way to remember this is that the first word in these matrix cells is false if it's a classifier error, or true if it's a classifier success. The second word is negative if the true label is negative, and positive if the true label is positive. Another name for a false positive that you might know from statistics is a type 1 error, and another name for a false negative is a type 2 error. We're going to use these 2-letter combinations, TN, FN, FP, and TP, as variable names when defining some new evaluation metrics shortly. We'll also use capital N here to denote the total number of instances of the sum of all the values in the matrix, the number of data points we're looking at. This matrix of all combinations of predicted label and true label is called the confusion matrix. We can take any classifier prediction on a data instance and associate it with one of these matrix cells depending on the true label of the instance and the classifier's predicted label. This also applies to multi-class classification, in addition to the special case of binary classification I've shown here. In the multi-class case with k classes, we simply have a k by k matrix instead of a 2 by 2 matrix. scikit-learn makes it easy to compute a confusion matrix for your classifier. Let's take a look at the notebook. Here we import the confusion matrix class from sklearn.metrics. We're going to use the same training set from the digits dataset with the binary imbalance labels that we created earlier. To get the confusion matrix, we simply pass the y-test set of predicted labels and the y-predicted set of predicted labels, and then print the output. The order of the cells of the little matrix output here is the same as the one I just showed on the slide. True negative and false negative are in the first column, and true positive and false positive are in the second column. In particular, the successful predictions of the classifier are on the diagonal, where the true class matches the predicted class. The cells off the diagonal represent errors of different types. Here we compute the confusion matrices for different choices of classifier in the problem, so we can see how they shift slightly with different choices of model. And this gives us some insight into the nature of the successes and failures observed for each type of classifier. So first we'll apply the most frequent class dummy classifier we saw earlier. What we can see here is that the right column that represents cases where the classifier predicted the positive class is all 0, which makes sense for this dummy classifier because it's always predicting the negative class, the most frequent one. We see that 407 instances are true negatives, and there are 43 errors that are false negatives. Here we apply the stratified dummy classifier that gives random output in proportion to the ratio of labels in the training set. Now the right column is no longer all 0 because this dummy classifier does occasionally predict the positive class. If we add the numbers in the right column, we see that 32 plus 6 equals 38 times the number of times the classifier predicted the positive class. Of those times, in 6 cases, the lower right diagonal, this was a true positive. In the next case, we'll apply a support vector classifier with linear kernel and C parameter equal to 1. We note that looking along the diagonal compared to the stratified dummy classifier above, which had a total of 375 plus 6, or 381 correct predictions, the support vector classifier has a total of 402 plus 38, which is 440 correct predictions on the same data set. Likewise, we can apply a logistic regression classifier, and that obtains similar results to the support vector classifier. And finally, we can apply a decision tree classifier and look at the confusion matrix that results from that. One thing we notice is that unlike the support vector or logistic regression classifier, which had balanced numbers of false negatives and false positives, the decision tree makes more than twice as many false negative errors, 17 of them actually, as false positive errors, of which there are 7. Now that we've seen how a confusion matrix can give us a little more information about the types of errors a classifier makes, we're ready to move ahead and define some new types of evaluation metrics that use information from the confusion matrix to give different perspectives on classifier performance. So let's go back to the matrix of possible binary classification outcomes, this time filled out with the actual counts from the notebook's decision tree output. Remember, our original motivation for creating this matrix was to go beyond a single number, accuracy, to get more insight into the different types of prediction successes and failures of a given classifier. Now we have these 4 numbers that we can examine and compare manually. Let's look at this classification result visually to help us connect these 4 numbers to a classifier's performance. What I've done here is plot the data instances by using 2 specific feature values out of the total 64 feature values that make up each instance in the digits dataset. The black points here are the instances with true class positive, namely the digit 1, and the white points have true class negative, that is, they're all the other digits except for 1. The black line shows a hypothetical linear classifier's decision boundary for which any instance to the left of the decision boundary is predicted to be in the positive class, and everything to the right of the decision boundary is predicted to be in the negative class. The true positive points are those black points in the positive prediction region, and false positives are those white points in the positive prediction region. Likewise, true negatives are the white points in the negative prediction region, and false negatives are black points in the negative prediction region. We've already seen one metric that can be derived from the confusion matrix counts, namely accuracy. The successful predictions of the classifier, the ones where the predicted class matches the true class, are along the diagonal of the confusion matrix. So if we add up all the counts along the diagonal, that will give us the total number of correct predictions across all classes. And dividing this sum by the total number of instances gives us accuracy. But let's look at some other evaluation metrics we can compute from these four numbers. Well, a very simple related number that's sometimes used is classification error, which is the sum of the counts off the diagonal, namely all of the errors divided by total instance count. And numerically, this is equivalent to just 1 minus the accuracy. Now for a more interesting example, let's suppose, going back to our medical tumor detecting classifier, that we wanted an evaluation metric that would give higher scores to classifiers that not only achieved a high number of true positives, but also avoided false negatives, that is, that rarely failed to detect a true cancerous tumor. Recall, also known as the true positive rate, sensitivity, or probability of detection, is such an evaluation metric, and it's obtained by dividing the number of true positives by the sum of true positives and false negatives. You can see from this formula that there are two ways to get a larger recall number. First, by either increasing the number of true positives or by reducing the number of false negatives, since this will make the denominator smaller. In this example, there are 26 true positives and 17 false negatives, which gives a recall of 0.6. Now suppose that we have a machine learning task where it's really important to avoid false positives. In other words, we're fine with cases where not all true positive instances are detected, but when the classifier does predict the positive class, we want to be very confident that it's correct. A lot of customer-facing prediction problems are like this. For example, predicting when to show a user a query suggestion in a web search interface might be one such scenario. Users will often remember the failures of a machine learning prediction, even when the majority of predictions are successes. One natural question that comes up when learning about precision and recall is when to apply them. In deciding what metric to use, a key question to ask is it more important in your scenario to avoid false positives or false negatives? In general, precision is used as a metric when our objective is to minimize false positives, and recall is used when the objective is to minimize false negatives. One possible scenario that illustrates when it could be important to avoid too many false positives is one where law enforcement is using a video recognition algorithm for finding likely criminals in a given area. In this case, a false positive would mean arresting an innocent person, and that may be considered a lot more damaging than a false negative, which would be letting a potential criminal walk free. So this is a precision-oriented task that should minimize false positives. On the other hand, a scenario where we might want to minimize false negatives is one where a law firm is searching for every possible email mentioning a certain event or person as part of a lawsuit, let's say. If we consider the positive class for the classification problem to be finding emails that have critical information, we want to avoid misclassification errors that incorrectly label an email as not containing critical information. In other words, we want to avoid false negatives. This is because missing even one critical email could omit valuable evidence. So casting a wider net like this will find more false positives, in other words, emails that are actually not relevant, but that's okay in this scenario because we have experts who can filter them out later. So this is a recall-oriented task that should minimize false negatives. So precision is an evaluation metric that reflects this situation, and it's obtained by dividing the number of true positives by the sum of true positives and false positives. So to increase precision, we must either increase the number of true positives the classifier predicts, or reduce the number of errors where the classifier incorrectly predicts that a negative instance is in the positive class. Here, the classifier has made 7 false positive errors, and so the precision is 0.79. Another related evaluation metric that will be useful is called the false positive rate. This gives the fraction of all negative instances the classifier incorrectly identifies as positive. Here, we have 7 false positives, which out of a total of 407 negative instances, gives a false positive rate of 0.02. The statistic commonly known as specificity is just 1 minus the false positive rate. Going back to our classifier visualization, let's look at how precision and recall can be interpreted. The numbers that are in the confusion matrix here are derived from this classification scenario. We can see that a precision of 0.68 means that about 68% of the points in the positive prediction region to the left of the decision boundary, or 13 out of the 19 instances, are correctly labeled as positive. A recall of 0.87 means that of all true positive instances, so all black points in the figure, the positive prediction region has quote-unquote found about 87% of them, or 13 out of 15. If we wanted a classifier that was oriented towards higher levels of precision, like in the search engine query suggestion task, we might want a decision boundary instead that looked like this. Now, all the points in the positive prediction region, 7 out of 7, are true positives, giving us a perfect precision of 1.0. Now, this comes at a cost because out of the 15 total positive instances, 8 of them are now false negatives. In other words, they're incorrectly predicted as being negative. And so recall drops to 7 divided by 15, or 0.47. On the other hand, if our classification task is like the tumor detection example, we want to minimize false negatives and obtain high recall, in which case we would want the classifier's decision boundary to look more like this. Now, all 15 positive instances have been correctly predicted as being in the positive class, which means these tumors have all been detected. However, this also comes with a cost, since the number of false positives, things that the detector triggers as possible tumors, for example, that are actually not, has gone up. So recall is a perfect 1.0 score, but the precision has dropped to 15 out of 42, or 0.36. These examples illustrate a classic trade-off that often appears in machine learning applications, namely that you can often increase the precision of a classifier, but the downside is that you may reduce recall. Or you could increase the recall of a classifier, but at the cost of reducing precision. Recall-oriented machine learning tasks include medical and legal applications where the consequences of not correctly identifying a positive example can be high. Often in these scenarios, human experts are deployed to help filter out the false positives that almost inevitably increase with high recall applications. Many customer-facing machine learning tasks, as I just mentioned, are often precision-oriented, since here the consequences of false positives can be high. For example, hurting the customer's experience on a website by providing incorrect or unhelpful information. Examples include search engine ranking and classifying documents to annotate them with topic tags. When evaluating classifiers, it's often convenient to compute a quantity known as an F1 score that combines precision and recall into a single number. Mathematically, this is based on the harmonic mean of precision and recall using this formula. After a little bit of algebra, we can rewrite the F1 score in terms of the quantities that we saw in the confusion matrix: true positives, false negatives, and false positives. This F1 score is a special case of a more general evaluation metric known as an F-score that introduces a parameter beta. By adjusting beta, we can control how much emphasis in the evaluation is given to precision versus recall. For example, if we have precision-oriented users, we might set beta equal to 0.5. since we want false positives to hurt performance more than false negatives. For recall-oriented situations, we might set beta to a number larger than 1, say 2, to emphasize that false negatives should hurt performance more than false positives. The setting of beta equals 1 corresponds to the F1 score special case that we just saw that weights precision and recall equally. Let's take a look now at how we can compute these evaluation metrics in Python using scikit-learn. Scikit-learn metrics provides functions for computing accuracy, precision, recall, and F1 score as shown here in the notebook. The input to these functions is the same. The first argument, here yTest, is the array of true labels of the test set data instances. And the second argument is the array of predicted labels for the test set data instances. Here we're using a variable called tree predicted, which are the predicted labels using the decision tree classifier in the previous notebook step. It's often useful when analyzing classifier performance to compute all of these metrics at once. So sklearn metrics provides a handy classification report function. Like the previous score functions, classification report takes the true and predicted labels as the first two required arguments. It also takes some optional arguments that control the format of the output. Here, we use the target names option to label the classes in the output table. You can take a look at the scikit-learn documentation for more information on the other output options. The last column, support, shows the number of instances in the test set that have that true label. Here we show classification reports for 4 different classifiers on the binary digit classification problem. The first set of results is from the dummy classifier, and we can see that as expected, both precision and recall for the positive class are very low, since the dummy classifier is simply guessing randomly, with low probability of predicting the positive class for the positive instances. Many classifiers in scikit-learn can provide information about the uncertainty associated with a particular prediction, either by using the decision function method or the predict proba method. When given a set of test points, the decision function method provides for each one a classifier score value that indicates how confidently the classifier predicts the positive class. So there will be large magnitude positive scores for those points. Or if it predicts a negative class, there'll be large magnitude negative scores for negative points. Here's an example in the notebook showing the first few instances from our classification problem using a logistic regression classifier. We can see that instances in the negative class often have large magnitude negative scores. And indeed, the instances in the positive class have positive scores from the logistic regression classifier. Likewise, the predict proba function provides predicted probabilities of class membership. Typically, a classifier would choose the more likely class. That is, in a binary classifier, the class with probability greater than 50%. Adjusting this decision threshold affects the predictions of the classifier. A higher threshold means the classifier has to be more confident in predicting the class. For example, we might predict class 1 only if the estimated probability of class 1 was over 70%, and this results in a more conservative classifier. Here's an example of getting these prediction probabilities for the test instances for the same logistic regression classifier. You can see that many entries with a positive label of 1 have a high probability like 0.995, while many negative label instances have a very low prediction probability. Note that not all models provide useful probability estimates of this type. For example, a model that was overfit to a training set might provide overly optimistic high probabilities that were in fact not accurate. Now we can use these decision scores or prediction probabilities for getting a more complete evaluation picture of a classifier's performance. For a particular application, we might pick a specific decision threshold depending on whether we want the classifier to be more or less conservative about making false positive or false negative errors. It might not be entirely clear when developing a new model what the right decision threshold will be, and how that choice will affect evaluation metrics like precision and recall. So instead, what we'll do is look at how the classifier performs for all possible decision thresholds. This example shows how that works. On the left here is a list of test instances with their true label and classifier score. If we set a decision threshold, then all the instances above that line, so for example, if we set the decision threshold to be -20 here, then all the instances above the line are below the threshold of -20, so -20 or less. And all the instances in this direction are above the threshold of -20. And so the ones below the threshold will be predicted to be in the negative class, and the ones above the threshold will be predicted to be in the positive class. So if we pick a specific threshold, so in this case -20, and we partition the test points in this way, we can compute precision and recall for the points that are predicted to be in the positive class. So in this case, we have 12 instances here, 12 total instances that are being predicted as positive, and only 4 of them, this one, this one, this one, and this one, are actually positive. And so the precision here is 4 divided by 12, or approximately 0.34. The recall, on the other hand, there are 4 positive labeled instances in the whole set of test examples here, and we found all of them with this particular threshold setting. So the recall here is 4 out of 4. We found all 4 positive labeled examples. And so for this particular threshold of -20, we can obtain precision and recall score for that threshold. Let's pick a different threshold. Let's look at what happens when the threshold is -10, right here. So again, anything below this line is treated, it has a higher value than -10 here, so those would be treated as positive predictions. Things above the line have a score below -10, so these would be predicted to be negative. And again, we can compute a precision and recall for this decision threshold setting. And we can see here that there are a total of 6 instances in the positive prediction class, of which 4 are actually of the positive class. And so the precision here is 4/6, or about 0.67. And again, the recall here is going to be 4 out of 4, and it's going to be 1.0 again. And so that corresponds to this point in the table over here. And then as we're computing these different precisions and recalls for different thresholds, we can also plot them on this precision recall chart. So the first pair of precision and recall numbers that I got, 0.34 and 1.0, we can plot on this point in precision recall space. The second example, so this was for the threshold of -20. When the threshold was -10, we got precision of 0.67 and a recall of 1, corresponding to this point that we can plot. And so you can see that if we do this for a number of other thresholds, for example, the threshold of 0, we'll get a precision of 0.75 and a recall of 0.75 that corresponds to this point, and that choice of decision threshold. And we can keep doing that for different thresholds. And we actually are plotting a series of points through the space, which can be connected as a curve. And so in this way, we can get a more complete picture by varying the threshold of how the precision and recall of the resulting classifier output changes as a function of the decision threshold. And this resulting chart here is called a precision recall curve. And we'll look at it in more detail next. Precision recall curves are a very widely used evaluation method for machine learning. As we just saw in the example, the x-axis shows precision and the y-axis shows recall. Now, an ideal classifier would be able to achieve perfect precision of 1.0 and perfect recall of 1.0. So the optimal point would be up here in the top right. And in general, with precision recall curves, the closer, in some sense, the curve is to the top right corner, the more preferable it is, the more beneficial the trade-off it gives between precision and recall. And we saw some examples already of how there is a trade-off between those two quantities, between precision and recall, with many classifiers. This example here is an actual precision recall curve that we generated using the following notebook code. The red circle indicates the precision and recall that's achieved when the decision threshold is 0. So I created this curve using exactly the same method as we saw in the previous example by looking at the decision function output from a support vector classifier, applying varying decision boundary, and looking at how the precision and recall changed as the decision boundary changed. Now, fortunately, scikit-learn has a function that's built in that does all of that, that can compute a precision and recall curve. And that's what we've been using in the notebook here. So you can see that in this particular application, there is a general downward trend. So as the precision of the classifier goes up, the recall tends to go down. In this particular case, you'll see also that it's not exactly a smooth curve. There are these sort of jaggy areas here, and in fact, it gets sort of the jumps tend to get a little bigger as we approach maximum precision. And this is a consequence of how the formulas for precision and recall are computed. They use discrete counts that include the number of true positives. And so as the decision threshold increases, there are fewer and fewer points that remain as positive predictions. So the fractions that are computed for these smaller numbers can change pretty dramatically with small changes in the decision threshold. And that's why these sort of trailing edges of the precision recall curve can appear a bit jagged when you plot them. ROC curves, or receiver operating characteristic curves, are a very widely used visualization method that illustrate the performance of a binary classifier. ROC curves on the x-axis show a classifier's false positive rate, so that would go from 0 to 1.0. And on the y-axis, they show a classifier's true positive rate, so that would also go from 0 to 1.0. It's worth mentioning here that the y-axis of the ROC curve plot is just the recall metric. The ideal point in ROC space is one where the classifier achieves 0, a false positive rate of 0, and a true positive rate of 1. So that would be the upper left corner. So curves in ROC space represent different trade-offs as the decision boundary, decision threshold is varied for the classifier. So just as in the precision recall case, as we vary decision threshold, we'll get different numbers of false positives and true positives that we can plot on a chart. So the dotted line here that I'm showing is the classifier curve that results, the ROC curve that results from a classifier that simply randomly guesses the label for a binary class. So it's basically like flipping a coin. So if you have two classes with equal numbers of positive and negative instances, then flipping a coin will get you randomly equal numbers of false positives and true positives for large data sets. So the dotted line here is used as a baseline. So a bad classifier will have performance that is random or maybe even worse than random, or maybe slightly better than random. A reasonably good classifier will give an ROC curve that is consistently better than random across all decision threshold choices. And then an excellent classifier would be one like I've shown here, which is way up and to the left. This particular example is an example of a logistic regression classifier using the notebook example that you've seen. So the shape of the curve can be important as well. The steepness of the curve. We want classifiers that maximize the true positive rate while minimizing the false positive rate. Now, as we'll see next, we can quantify the goodness of a classifier in some sense by looking at how much area there is underneath the curve. So the area underneath the random classifier is going to be 0.5. But then the area, as you can see, the size, the bumpiness of the classifier as it approaches the top left corner, the area underneath the curve will get larger and larger, and it'll approach 1. And so, as we'll see in the next slide, we use something called area under the curve, AUC. That's a single number that measures this total area underneath the ROC curve as a way to summarize a classifier's performance. So an AUC of 0 represents a very bad classifier, and an AUC of 1 will represent an optimal classifier. Like any other evaluation metric, AUC has advantages and disadvantages. Its advantages include the fact that AUC gives a single number, which makes it easy to compare classifiers. Another advantage is that AUC does not require specifying a particular decision threshold. Instead, you can think of AUC as a summary of the performance of a classifier over all possible decision thresholds. On the other hand, like any other single number metric, AUC loses information about classifier trade-offs and the shape of the ROC curve. It might be that two classifiers have similar AUC, but have overlapping ROC curves with different shapes in different areas. For example, it might be important to achieve very low false positive rates for a specific range of true positive rates. But using only AUC would not be able to necessarily detect those kinds of more subtle performance differences. Now that we've looked at evaluation of binary classifiers, let's take a look at how the more general case of multi-class classification is handled in evaluation. So, in many respects, multi-class evaluation is a straightforward extension of the methods we use in binary evaluation. Instead of two classes, we have multiple classes, so the results for a multi-class evaluation amount to a collection of true versus predicted binary outcomes per class. And just as we saw in the binary case, you can generate confusion matrices in the multi-class case. They're especially useful when you have multiple classes because there are many different kinds of errors that result from one true class being predicted as a different class. So we'll look at an example of that. Classification reports that we saw in the binary case are easy to generate for the multi-class case. Now, the one area which is worth a little more examination is how averaging across classes takes place. There are different ways to average multi-class results that we'll cover shortly. The support, the number of instances for each class, is important to consider. So just as we were interested in how to handle imbalanced classes in the binary case, it's important, as we'll see, to consider a similar issue of how the support for classes might vary to a large or small extent across multiple classes. There is a case of multi-label classification in which each instance could have multiple labels. For example, a web page might be labeled with different topics that come from a predefined set of areas of interest. We won't cover multi-label classification in this lecture. Instead, we'll focus exclusively on multi-class evaluation. The multi-class confusion matrix is a straightforward extension of the binary classifier 2x2 confusion matrix. For example, in our digits dataset, There are 10 classes for the digits 0 through 9. So the 10-class confusion matrix is a 10 by 10 matrix with the true digit class indexed by row and the predicted digit class indexed by column. As with the 2 by 2 case, the correct predictions by the classifier, where the true class matches the predicted class, are all along the diagonal, and misclassifications are off the diagonal. In this example, which was created using the following notebook code, based on a support vector classifier with linear kernel, we can see that most of the predictions are correct, with only a few misclassifications here and there. The most frequent type of mistake here was apparently misclassifying the true digit 8 as a predicted digit 1, which happened 3 times. And indeed, the overall accuracy is high, about 97%, as shown here. As an aside, it's sometimes useful to display a confusion matrix as a heat map in order to highlight the relative frequencies of different types of errors. So I've included the code to generate that here. For comparison, I've also included a second confusion matrix on the same dataset for another support vector classifier that does much worse in a distinctive way. The only change is to use an RBF radial basis function kernel instead of a linear kernel. While we can see from the accuracy number of about 49% below the confusion matrix that the classifier is doing much worse than with the linear kernel, that single number doesn't give much insight into why. Looking at the confusion matrix, however, reveals that for every true digit class, a significant fraction of outcomes are to predict the digit 4. That's rather surprising. For example, of the 44 instances of the true digit 2 in row 2, 17 are classified correctly, but 27 are classified as the digit 4. Clearly something is broken with this model, and I picked this second example just to show an extreme example of what you might see when things go quite wrong. This digits dataset is well established and free of problems, but especially when developing with a new dataset, seeing patterns like this in a confusion matrix could give you valuable clues about possible problems, say in the feature preprocessing, for example. So as a general rule of thumb, as part of model evaluation, I suggest always looking at the confusion matrix for your classifier to get some insight into what kinds of errors it is making for each class, including whether some classes are much more prone to certain kinds of errors than others. Next, just as in the binary case, you can get a classification report that summarizes multiple evaluation metrics for a multi-class classifier, with an average metric computed for each class. Now, what I'm about to describe also applies to the binary class case, but it's easier to see when looking at a multi-class classification problem with several classes. Let's look at a specific example of micro versus macro averaging using our fruit data set. So with macro averaging, we're treating each class as if it has equal weight in the overall calculation. So what we need to do is we first compute a metric. So in this case, we're going to compute precision with each class separately. And then once we've done that for each class, then we'll average the results across all the classes to get the final macro average precision number. So what we do is we take a look at, for each of the classes, we look at all the cases where the classifier predicted that a particular piece of fruit was going to be an orange. But then we look at the true class to see how many times, since we're computing precision, how many times that it was actually an orange. So in this case, the classifier predicted orange correctly 1 time out of 5. The rest of the time it seemed to be very confused and predicted lemons and apples. So the precision for the orange class was 1/5 or 0.2. We can do the same thing for the lemon class. So every time the classifier predicted lemons, we can see that it got one example correct and one example incorrect. So it had a precision for the lemon class of 1/2 or 0.5. And similarly, For apples, it always predicted the true class. So it got perfect precision or 1.0. So these are the precisions for each class, and to compute the macro average precision, we then just average the precisions that we got for the classes, and that turns out to be, in this case, 0.57. When we compute micro averages, on the other hand, we give each instance in the data set equal weight, so that classes with the most instances, the largest ones, have the most influence in the final micro average number. So here we're going to compute micro average precision. And to do that, we don't need to consider each class separately anymore. We can simply aggregate all the outcomes across all the classes and compute precision across the aggregate outcomes. So all that means is we just take all 9 examples that we have here. We look to see how many the predicted class matched the true class. So in this case, we have 4 correct predictions. 4 correct predictions out of 9 total instances. And so that gives us a micro average precision of 0.44. If the classes have about the same number of instances, macro and micro average will be about the same. If some classes are much larger, have more instances than others, and you want to weight your metric toward the largest ones, use micro averaging. If you want to weight your metric towards the smallest classes, use macro averaging. If the micro average is much lower than the macro average, then examine the larger classes for poor metric performance. If the macro average is much lower than the micro average, then you should examine the smaller classes to see why they have poor metric performance. Here we use the average parameter on the scoring function. In the first example, we use the precision metric and specify whether we want micro average precision, which is the first case, or macro average precision in the second case. In the second example, we use the F1 metric and compute micro and macro averaged F1. Now that we've seen how to compute these metrics, let's take a look at how to use them to do model selection. We saw that for classification, because there were some scenarios like medical diagnostic predictions or customer-facing website features, where the consequences of false positives were very different than false negatives, it made sense to distinguish these types of errors and do a more detailed analysis. In evaluating classifiers, for example, we looked at plots like precision recall curves that could show the trade-offs a classifier could achieve between making errors of those two types. In theory, we could apply the same type of error analysis and more detailed evaluation to regression that we applied for classification. For example, we could analyze the regression model's predictions and categorize errors of one type, where the regression model's predicted value was much larger than the target value, compared to a second error type where the predicted value was much smaller than the target value. In practice, though, it turns out that for most applications of regression, distinguishing between these types of different errors is not as important. This simplifies evaluation for regression quite a bit. In most cases, the default R-squared score that's available for regression in scikit-learn and that summarizes how well future instances will be predicted is adequate for most tasks. As a reminder, the R-squared score for a perfect predictor is 1.0, and for a predictor that always outputs the same constant value, the R-squared score is 0. The R-squared score, despite the squared in the name that suggests it's always positive, does have the potential to go negative for bad model fits, such as when fitting nonlinear functions to data. There are a few alternative regression evaluation metrics you should be aware of that work a bit differently than the R-squared score. Mean absolute error takes the mean absolute difference between the target and predicted values. In machine learning terms, this corresponds to the expected value of the L1 norm loss. This is sometimes used, for example, to assess forecast outcomes for regression in time series analysis. Mean squared error takes the mean squared difference between the target and predicted values, and this corresponds to the expected value of the L2 norm loss. This is widely used for many regression problems, and larger errors have correspondingly larger squared contributions to the mean error. Like mean absolute error, mean squared error doesn't distinguish between over and under estimates. Finally, one situation that does arise quite often is the existence of outliers in the data, which can have unwanted influence on the overall R-squared or mean score value. So in those cases, when ignoring outliers is important, you can use the mean absolute error score, which is robust to the presence of outliers because it uses the median of the error distribution rather than the mean. We saw how using dummy classifiers could give us simple but useful baselines to compare against when evaluating a classifier. The same functionality exists for regression. There is a dummy regressor class that provides predictions using simple strategies that do not look at the input data. This example, which is available as the regression example from this lecture's notebook, shows a scatter plot using data based on a single input variable, which is plotted along the x-axis, from the diabetes dataset. The points are the data instances from the test split and form a cloud that looks like it may trend down slightly to the right. The green line, which is also labeled fitted model, is the default linear regression that was fit to the training points. We can see that it's not a particularly strong fit to the test data. The red line, labeled dummy mean, shows a linear model that uses the strategy of always predicting the mean of the training data. So this is an example of a dummy regressor. You can look at the notebook to see that a dummy regressor is created and used just like a regular regression model. You create, fit with the training data, and then call predict on the test data. Although again, like the dummy classifier, you should not use the dummy regressor for actual problems. Its only use is to provide a baseline for comparison. Looking at the regression metrics output from the linear model compared to the dummy model, we can see that as expected, the dummy regressor achieves an R-squared score of 0, since it always makes a constant prediction without looking at the output. In this instance, the linear model provides only slightly better fit than the dummy regressor according to both mean squared error and the R-squared score. Aside from the strategy of always predicting the mean of the training target values, you can also create some other flavors of dummy regressors that always predict the median of the training target values, or a particular quantile of those values, or a specific custom constant value that you provide. Although regression typically has simpler evaluation needs than classification, it does pay to double check to make sure the evaluation metric you choose for a regression problem does penalize errors in a way that reflects the consequences of those errors for the business, organizational, or user needs of your application. Now that you've seen a number of different evaluation metrics for both binary and multi-class classification, let's take a look at how you can apply them as criteria for selecting the best classifier for your application, otherwise known as model selection. In previous lectures, we've seen a number of different evaluation frameworks for potential model selection. First, we simply did training and testing on the same dataset, which, as we well know, typically overfits badly and doesn't generalize well to new data. As a side note, however, it can serve as a useful sanity check to make sure your software engineering and feature generation pipeline is working correctly. Second, we frequently used a single train test split to produce a single evaluation metric. While fast and easy, This doesn't give as realistic a set of estimates for how well the model may work on future new data, and we don't get a good picture for the variance in the evaluation metrics that may result as we do prediction on different test sets. Third, we used k-fold cross-validation to create k-random train test splits where the evaluation metric was averaged across splits. This leads to models that are more reliable on unseen data. In particular, we can also use grid search using, for example, the grid search CV method within each cross-validation fold to find optimal parameters for a model with respect to the evaluation metric. The default evaluation metric used for a cross-val score or grid search CV is accuracy. So how do you apply the new metrics you've learned about here, like AUC, in model selection? scikit-learn makes this very easy. You simply add a scoring parameter that's set to the string with the name of the evaluation metric you want to use. Let's first look at an example using the scoring parameter for cross-validation, and then we'll take a look at the other primary method of model selection, grid search. In the notebook here, we have a cross-validation example where we're running 5 folds using a support vector classifier with a linear kernel and C parameter set to 1. The first call to cross-val score just uses default accuracy as the evaluation metric. The second call uses the scoring parameter using the string ROC_AUC, and this will use AUC as the evaluation metric. The third call sets the scoring parameter to recall, to use that as the evaluation metric. You can see the resulting list of 5 evaluation values, 1 per fold for each metric. Now here we're not doing any parameter tuning, we're simply evaluating our model's average performance across multiple folds. Now in this grid search example, we use a support vector classifier that uses a radial basis function kernel. And the critical parameter here is the gamma parameter that intuitively sets the radius or width of influence of the kernel. We use grid search CV to find the value of gamma that optimizes a given evaluation metric in 2 cases. In the first case, we just optimize for average accuracy. In the second case, we optimize for AUC. In this particular case, the optimal value of gamma happens to be the same, 0.001, for both evaluation metrics. But as we'll see later, in other cases, the optimal parameter value can be quite different depending on the evaluation metric used to optimize. You can see the complete list of names for the evaluation metrics supported by the scoring parameter by running the following code that uses the scores variable imported from sklearn metrics. You can see metrics for classification, such as the string precision_micro that represents micro-average precision, as well as metrics for regression, such as the R2 metric for R² regression loss. Let's take a look at a specific example that shows how a classifier's decision boundary changes when it's optimized for different evaluation metrics. This classification problem is based on the same binary digit classifier training and test sets we've been using as an example throughout the notebook. In these classification visualization examples, the positive examples, the digit 1, are shown as black points, and the region of positive class prediction is shown in the light-colored or yellow region to the right of the decision boundary. The negative examples, all other digits, are shown as white points, and the region of negative class prediction here in these figures is to the left of the decision boundary. The data points have been plotted using 2 out of the 64 feature values in the digits dataset, and have been jittered a little, that is, I've added a little bit of random noise so we can see more easily the density of examples in the feature space. Here's the scikit-learn code that produced this figure. We apply grid search here to explore different values of the optional class weight parameter that controls how much weight is given to each of the 2 classes during training. As it turns out, optimizing for different evaluation metrics results in different optimal values of the class weight parameter. As the class weight parameter increases, more emphasis will be given to correctly classifying the positive class instances. The precision-oriented classifier we see here, with class weight of 2, tries hard to reduce false positives while increasing true positives. So it focuses on the cluster of positive class points in the lower right corner, where there are relatively few negative class points. Here, precision is over 50%. In contrast, the recall-oriented classifier, with class weight of 50, tries hard to reduce the number of false negatives while increasing true positives. That is, it tries to find most of the positive class points as part of its positive class predictions. We can also see that the decision boundary for the F1-oriented classifier has an optimal class weight of 2, which is between the optimal class weight values for the precision and recall-oriented classifiers. Visually, we can see that the F1-oriented classifier also has a kind of intermediate positioning between the precision and recall-oriented decision boundaries. This makes sense, given that F1 is the harmonic mean of precision and recall. The AUC-oriented classifier, with optimal class weight of 5, has a similar decision boundary to the F1-oriented classifier, but shifted slightly in favor of higher recall. We can see the precision-recall trade-off very clearly for this classification scenario in the precision recall curve for the default support vector classifier with linear kernel optimized for accuracy on the same dataset, and using the balanced option for the class weight parameter. Let's take a look at the code that generated this plot. Take a moment to imagine how the extreme lower right part of the curve on this precision recall curve represents a decision boundary that's highly precision-oriented in the lower right of the classification plot where there's a cluster of positive examples. As the decision threshold is shifted to become less and less conservative, tracing the curve up and to the left, the classifier becomes more and more like the recall-oriented support vector classifier example. Again, the red circle represents the precision recall trade-off achieved at the 0 score mark, which is the actual decision boundary chosen for the trained classifier. For simplicity, we've often used a single train test split in showing examples of evaluation scoring. However, using only cross-validation or a test set for model selection or parameter tuning may still lead to more subtle forms of overfitting and thus optimistic evaluation estimates for future unseen data. An intuitive explanation for this might be the following. Remember that the whole point of evaluating on a test set is to estimate how well a learning algorithm might perform on future unseen data. The more information we see about our data set as part of repeated cross-validation passes in choosing our model, the more influence any potential held-out test data has played into selecting the final model, not merely evaluating it. This is sometimes called data leakage, and we'll describe more about that phenomenon in another module. So we haven't done an evaluation with truly held-out test set unless we commit to holding back a test split that isn't seen by any process until the very end of the evaluation. So that's what's actually done in practice. There are 3 data splits: training for model building, validation for model selection, and a test set for the final evaluation. The training and test sets are typically split out first, and then cross-validation is run using the training data to do model and parameter selection. Again, the test set is not seen until the very end of the evaluation process. Machine learning researchers take this protocol very seriously. The train, validate, test design is a very important, universally applied framework for effective evaluation of machine learning models. That brings us to the end of this section of the course on evaluation for machine learning. You should now understand why accuracy only gives a partial picture of a classifier's performance, and be more familiar with the motivation and definition of important alternative evaluation methods and metrics in machine learning, like confusion matrices, precision, recall, F1 score, and area under the ROC curve. You've also seen how to apply and choose these different evaluation metric alternatives in order to optimize model selection or parameter tuning for a classifier to maximize a given evaluation metric. Finally, I'd like to leave you with a couple of points. First, simple accuracy may not often be the right goal for your particular machine learning application. As we saw, for example, with tumor detection or credit card fraud, false positives and false negatives might have very different real-world effects for users or for organization outcomes. So it's important to select an evaluation metric that reflects those user, application, or business needs. Second, there are a number of other dimensions along which it may be important to evaluate your machine learning algorithms that we don't cover here, but that are important for you to be aware of. I'll mention two specifically here. Learning curves are used to assess how a machine learning algorithm's evaluation metric changes or improves as the algorithm gets more training data. Learning curves may be useful as part of a cost-benefit analysis. Gathering training data in the form of labeled examples is often time-consuming and expensive, so being able to estimate the likely performance improvement of your classifier, if you say invest in doubling the amount of training data, can be a useful analysis. Second, sensitivity analysis amounts to looking at how an evaluation metric changes as small adjustments are made to important model parameters. This helps assess how robust the model is to choice of parameters. This may be important to perform, especially if there are other costs, such as runtime efficiency, that are critical variables when deploying an operational system that are correlated with different values of parameter, for example, decision tree depth or feature value threshold. In this way, a more complete picture of the trade-offs achievable across different performance dimensions can help you make the best practical deployment decisions for your machine learning model. So you've probably seen already that many families of machine learning model make their predictions by outputting a probability. For example, if we have a binary classification problem, we might use logistic regression, which is trained to output the probability that the input data point belongs to the positive class. Naive Bayes is another example that outputs a probability. Having a model being able to make predictions in terms of probabilities is very useful. For example, if the classifier is being used as part of some important decision-making process, the prediction probability can be treated as a sort of confidence estimate that the classifier has in its prediction. So if we're going to rely on those probability or confidence values, it's super important to make sure that these values are accurate in some sense. But what does it mean for probabilities to be accurate? And if a classifier isn't generating accurate probabilities, how can we fix it so that it does? Making sure a model's prediction probabilities are accurate is known as model calibration. So in this video, we'll look at what model calibration is in some detail, why it's super important, and how to implement model calibration to improve the accuracy of any classifier's output probabilities. So let's start by looking at what model calibration is. What is a calibrated model? Well, a calibrated model outputs prediction probabilities that are close to real-world observed probabilities. And there's a very familiar example that we can use to help understand this concept, and it comes from weather prediction. Suppose for all the days that a meteorologist predicted 100% chance of rain, it actually rained only 50% of the time. In this case, I think you'd agree that the meteorologist's probability estimate of 100% doesn't match the proportion that's actually observed in reality, which is 50%. So we would say that the meteorologist's predictions, their prediction probabilities, are not calibrated. A meteorologist's predictions would be calibrated if, across all the days where the weather person predicts it will rain with probability R%, it actually turns out that it does rain R% of the time. So we have two quantities here. We have the predicted probability. That's the probability that the meteorologist actually predicts when they say it's going to rain. So they predict an R% chance of rain. And then we have the empirical probability, which is the actual observed proportion of days that it actually rains when the meteorologist predicts an R% chance of rain. So again, the meteorologist's predictions are calibrated if the probabilities that they predict, their predicted probabilities, are equal to their empirical probabilities. The same concept that you can apply to a human making predictions, you can also apply to a machine learning model making predictions. So a machine learning model may also have calibration issues in exactly the same way. So for example, if we define a binary classification problem where we have an instance xi that has a label yi that can be 0 or 1, we say that a predictor f of xi is calibrated, and again, this is exactly the same as the weather example, if across all the data points where the predictor predicts that the point belongs to class 1 with probability R%, the data point actually does belong to class 1 exactly R% of the time. So it's the same as in the weather example. The predicted probability should match the empirical probability. So mathematically, we can write this equivalency that we're looking for a well-calibrated model using this notation. So for all the data points xi, for which the classification function f takes xi as input and predicts some probability p. So for example, in the binary classification problem, if the job of the classifier is to predict if it's going to rain tomorrow, the prediction might be 100%. And then we look at, so these are all the instances where the classifier predicts 100%. And then of those days, so for all the days that are in that set, we compute the average or the expectation over the actual labels, the labels of whether it actually did rain or not. So that's the empirical probability. So E here is a symbol in mathematics that typically means expected value in this context. So it's essentially, just think of it like an average in this case. What's the average label, 0, 1 label for the days where the predictor was 100%, of what was the average label across all those days? Was it 100%, in which case the classification probability is well calibrated, or was it 50% or some other value? So the requirement mathematically that the predicted probabilities from the predictor match the empirical probability is contained in this statement. So why is it important for a predictive model's probabilities to match reality? Why is it important that they be well calibrated? Well, there are a number of different scenarios that depend on having accurate prediction probabilities. As I mentioned before, if the classifier is being used as part of some important decision process, and this is typical in many scenarios, both in machine learning and in human decision making. That was a famous example of the risk assessments in the justice system that are done, that likelihood of a person reoffending. That's an example of a classifier being used in a human decision loop. So we need to know if those probabilities, those confidence estimates, are accurate, if they match reality. So it's important in any kind of decision-making scenario. Also, there are a lot of situations in machine learning where we want to compute the expectation or an average of an important quantity, like the expected number of clicks on a search result, the expected number of clicks on an advertisement, and so on. So if you want your expectation of that quantity to be valid, you want to make sure that the probabilities that go into that calculation are accurate. And finally, it's quite common these days to have larger systems that are modular and probabilistic. So all the models in a large system that rely on each other speak the common language of probability. For example, on the right here I have a spam email detection scenario where the input to the system is some email content. And the goal is to predict if this email is a spam email or not. That might involve more than one process. So you might have a separate classifier that predicts whether this email is urgent or important based on the content. And then that estimate of being urgent or important forms part of the feature set that goes into the final predictor, whether this is a spam email. So I think you'll agree that if you have a large system where the input probability from at one level comes from an earlier system, it's important for those probabilities to be accurate. It allows the system to adjust itself within each module, keeping the probabilities accurate without having to recalibrate the entire system. In some scenarios, it may not be as important to do calibration. So for example, if your goal is to rank a set of things, like ranking search results, where the ordering is important, but the raw, the probability of relevance for those is not as important to explicitly calculate, then in some cases you could rely on just the raw model prediction score, just making sure that the rankings were accurate, but not necessarily caring about the specific probability of relevance of each of the documents. So there may be some non-probabilistic frameworks where calibration may not be as important. But given the prevalence of statistical methods in many systems, it's important to understand for the parts of the system that do use probabilistic modules, that those modules are producing well-calibrated probabilities. And miscalibrated models are very common in machine learning, so you shouldn't assume that a model is calibrated right out of the box. And this is especially true for more complex models that use ensembles or boosting, for example. And finally, most estimators in a package like scikit-learn, for example, do provide output probabilities via the predict-proba method. But there are some classifiers that only implement, say, decision score. You can still get accurate output probabilities from those raw decision scores by performing calibration, and we'll talk a bit more about that in a minute. So one of the first steps in looking at a prediction model and how well calibrated it is to visualize the calibration situation. And we do this with something called calibration curves or reliability curves. So you remember I said that being well calibrated means having predicted probabilities that were equal to empirical probabilities. So that's exactly what a reliability curve or calibration curve shows. Along the x-axis, we have the predicted probabilities from a classifier. So we take all the instances for which it predicted a particular probability p, let's say 0.4, and put those into a bin. And then we compute the empirical probability and show that on the y-axis. So again, this is for all the day, in this case, all the days that were in the bin for which the classifier predicted a 0.4 chance of rain. You can draw a sort of straight line to indicate those days. The empirical probability is how many days it actually rained in that pool of days for which the classifier predicted a 40% chance of rain. So perfect calibration on the classification, in the classification scenario, on a calibration plot is given by the line y equals x, right? So that line y equals x is exactly the line where the predicted probability given by the classifier exactly equals the empirical probability, the actual percentage of time that it rained that we observed. So when we plot the predicted probability against the empirical probability, a perfectly calibrated classifier would give a calibration curve that was exactly a straight line along y equals x. And the less calibrated a classifier is, the more it will deviate from that line y equals x. So a classifier in this case, like a support vector machine, which is this green, the topmost green line, we can see that in some cases, the predicted probability of 0.6 actually understates the empirical probability. So instead of being an empirical probability of 0.6, what we actually observed was something closer to 0.8. And similarly, when the classifier predicted 0.3, the empirical probability turned out to be close to 0. In other words, when the classifier predicted 30% chance of rain, for all the days in that bucket, what we observed as the empirical probability was close to 0 instead of being 30%. So you can see that the support vector machine is quite poorly calibrated. You can see that some other models, like the logistic regression, for example, the blue line that tracks very closely the line y equals x, is already very well calibrated, so its predicted probabilities are very similar to what we actually observe the empirical probabilities to be. So a calibration curve is a great way to do a sort of a diagnostic on a classifier to understand how well calibrated it is. The more it deviates from the line y equals x, the less well calibrated it is. And the more closely it tracks the line y equals x, the better calibrated it is. So I'll describe in a minute how you can create these kinds of calibration curves with scikit-learn. But suppose for now that we've decided that the predictor is not well calibrated. What can we do about it? How can we fix these poorly calibrated probabilities? Well, one widely used approach is to treat the prediction model like a black box. In other words, we train a calibration function that learns to correct or improve the output prediction scores of an existing predictor and to turn it into a calibrated predictor. So we might have a prediction function f of x that produces some raw output, and the output could be a probability if the classifier supports the predict proba method, or it could be a score that comes out of the model, in which case you could get it from the decision function method. But in either case, let's assume that that raw prediction output is not calibrated. So we have this original model. What we're going to do is then we're going to take the output from the original model. So we're not going to modify the original model at all. We're simply going to take its output and learn a transformation function, let's call it g, that can turn the raw prediction output from the original model into a calibrated prediction probability. And we're going to learn this transformation function g using what's called a calibration set. So this is a set of data that must be different from the set of data that was used to train the original model. We'll talk about that more in a minute. A good calibration function, this function g, ideally should be strictly monotonic, should always be increasing in order to preserve the original prediction rankings. For example, if the raw score from the original model for item A is less than the raw score for item B, then we would expect that the prediction probability for item A should be less than the prediction probability for item B. And here I'm talking about say a binary classification scenario. So there are a couple widely used methods to learn this transformation function g. The first method is called Platt scaling or sigmoid calibration, where g is a sigmoid function. And then the second, more general method is called isotonic regression, and I'll explain what each of these is in the next slides. One simple but widely used method that's quite effective in some cases is called Platt scaling or sigmoid calibration. The original motivation for John Platt introducing this approach was that support vector machines typically give a raw prediction score. So they don't give probabilities as outputs. They give a score that's related to a point's position relative to the margin. But if we're in a situation like in spam email detection, for example, where we need a probability, we need a way to convert those raw prediction scores to class probabilities. And so what sigmoid calibration does is it fits a sigmoid curve to the points that are formed by combining the SVM raw prediction score and the empirical probability. So we can see in this example, in this chart, the x-axis shows the raw prediction score. Each of these points represents a data point that's to be classified, and the x-axis represents the raw prediction score that you get when you take an existing support vector machine and you ask it to give a score for a particular point. And then the class probability is the actual empirical probability that the points with that prediction score belong to the class, the average class prediction in a binary classification scenario. So if we plot these points for an SVM, we might get a sort of curve that looks somewhat like this, and it's roughly sigmoid shaped. So in this case, sigmoid calibration is a good way to approximate that curve. So more specifically, what we're doing with sigmoid calibration is we have the raw scores from some predictor f with input point x, and to learn the sigmoid function that best fits the observed relationship between the prediction score and the class probability. We just fit the sigmoid, which means finding the values for A and B that produce a sigmoid S-shaped curve that best approximates that set of observed points. And we can tune A and B to maximize the calibration accuracy, so getting the reliability curve as close as possible to the line y equals x in the plot. So plot scaling is especially effective for maximum margin type methods, such as support vector machines or boosted trees that already tend to have sigmoidal distortions in their predicted probabilities. The second and more general form of calibration method is called isotonic regression. So instead of assuming that the relationship between the predicted probability and the observed class fraction is a sigmoid, instead we use something called isotonic regression to obtain this function g. So in this plot on the right, we can see the original data points. So the x-axis is the score, just like before, the raw score from, let's say, a support vector machine. And just like before, the y-axis represents some kind of empirical estimate between 0 and 1 of the true empirical probability for all the items that have that score. So in this plot, you can see that the dots, the red dots, are the data points, and the green continuous line that is fit through the data points here, that is sort of a step-like function, is the isotonic fit. So isotonic regression is a way to get a sort of step-like regression function that captures the relationship in a way that guarantees a strictly increasing function. And you can compare the isotonic fit to these data points with a simple linear fit. So like most regression situations, a linear fit is good at capturing certain kinds of global trends, but isotonic regression can capture more complex structure in the observed relationship between the classifier score and the empirical probabilities. So once we learn this function g, that's the function that allows us to take a raw score in x and convert it to a calibrated probability. So we can just take our original estimate that came from f of x, we can pass it through the function g, the calibration function g that we learned, to get our calibrated probability estimate. So to compare the two again, plot regression is restricted to using a sigmoid to capture this relationship, but isotonic regression can fit any bias shape. It's a more powerful method, although it's also prone to overfitting if you have less than, say, 1,000 data points. So it's better to use it when you have larger data sets. So how is this all implemented in scikit-learn? Well, the main routine that you're going to want to use in scikit-learn for calibration is called calibrated classifier CV, and the CV stands for cross-validation. And the idea is you pass the base classifier you want to calibrate, you set some parameters that indicate the method you want to use for calibration, as well as the number of cross-validation folds to use for tuning. And the result is a calibrated version of the input classifier that you gave it. And calibrated classifier CV supports both of the methods that I just described, both the sigmoid calibration and isotonic calibration. Scikit-learn also has routines to generate the calibration curve that I showed you, where you can pass it the array of the true target values and the corresponding probabilities of the positive class, and then it will bin the given examples and compute the empirical and predicted probabilities for each bin of examples. In newer versions of scikit-learn, they have included a function called calibration display, for plotting these curves. So let's start with a scenario where you've already fitted a classifier, like a logistic regression classifier or a support vector machine, and you don't want to fit it, you just want to correct the output scores or probabilities so that they're well calibrated. So in this case, there's a parameter to calibrate a classifier CV called CV that indicates the method you want to use for cross-validation. If you set that to the value pre-fit, then it won't actually do cross-validation, so it won't split the data. It'll take all the data you provide when you call the fit method for calibrated classifier CV and use that to fit the regressor, the calibration regressor. So again, you have to ensure that the calibration data for fitting the calibration regressor is completely disjoint from the data you used to train the underlying prediction model. There's another setting called ensemble for calibrated classifier CV. I'll talk about that in a minute, but that setting is ignored if you specify pre-fit. So here's an example of using calibrated classifier CV when you already have a classifier that you've trained and you just want to make sure that the output scores or probabilities are well calibrated. So here I've made a toy example where I've created a toy classification problem using make classification. We're calling train test split here. Now note that in calling train test split, we have the X train and Y train as usual. But then what we normally call the test split, we're calling X calib and Y calib. And the reason for that is, as I said, you want to train the regressing function in the calibrated classifier using different data than you used to train the classifier. So we're going to fit this, in this case, a Gaussian naive Bayes model. We're going to train it using the training data, as usual. But then, to calibrate it, we're going to pass in the Gaussian naive Bayes classifier that we trained as the base estimator. And we're going to set this CV setting to pre-fit. And then when we ask in order to get the calibration going, we call the fit method on the calibrated classifier CV object. And the data we give it to do the calibration is the calibration set that we split off initially. So you can see it's a very straightforward process to take an existing classifier and correct its outputs so that you get better calibrated probabilities. Now let's look at the case where you have not yet trained the classifier, where you want to do the fitting and the calibrating simultaneously. So in this case, you set the CV setting to the cross-validation strategy you want. The default, if you don't specify any CV setting, is to use 5-fold cross-validation, which is stratified if the label that you're predicting is a binary or multi-class label. And you can set the ensemble parameter according to how you want to combine the results from each of these cross-validation folds. So I'm not going to go into too much detail here about all the different combinations of scenarios you can handle. You can see the scikit-learn documentation at the bottom of this slide for more details. So here's a quick example of how to use the calibrated classifier CV object to take a base classifier that has not yet been trained and to do the training and the calibration simultaneously using cross-validation. So in this case, I haven't specified the CV setting, so by default, it's going to do a stratified cross-validation. I did actually specify here that I want 5 folds. And the default behavior for the ensemble, I'll talk about in a minute. But basically, the workflow is very similar to the pre-trained classifier, except in this case, you're passing in all of the data that you have in order to fit that calibration regression model. So internally, what it'll do is it will do the 5 cross-validation fold splits with the 4 out of 5 parts that are the training data. It will train the classifier with those. And then with the remaining part, it will do the calibration. By default, for each cross-validation split, it fits a copy of the base estimator to the training set, and then it calibrates the result using the test set. And by default for prediction, when the ensemble equals true flag is on, then the predicted probabilities that come out of the calibrated classifier object are the averages across the individual calibrated classifiers. So you can see that when I call calibrated classifier CV with this base Gaussian naive Bayes model, the result, if I look at the property calibrated classifiers underscore, since I asked for 5-fold cross-validation, it will provide me 5 calibrated classifiers. And it's those 5 classifiers, if the ensemble equals true flag is on, it will combine the predicted probabilities across all those individual calibrated classifiers. It'll average those to give the final calibrated predicted probability for the overall calibrated classifier CV model. Okay, so just to wrap up on calibration, how do you integrate this calibration step into your workflow? Well, the first step is to decide whether calibration matters for your application. You should consider using a calibration if you have a probabilistic framework that you're working within, if there are important consequences to the accuracy of the probabilistic outputs, if they're being used as confidence or risk estimates in decision making, or if you have important expected values of quantities that you want to compute. You should always run the calibration step on a separate validation set that's different from the training set that was used originally to train the classifier. Otherwise, if you don't do this, then adding the calibration step could simply worsen any overfitting problems you might have. There are some other technical considerations that, for the sake of time, I didn't go into. The calibration function, in addition to ideally being strictly increasing, should also minimize what's called the strictly proper scoring rule. And it should also ideally maximize what's called the sharpness property. And that basically means that it should make predictions that are far from just the global probability average. So if you want more details, I provided a paper at the bottom of this slide that goes into more of those technical considerations. But to make sure that you use calibration correctly in your workflow, it's not as important to follow these last technical considerations. The most important things to remember are to always run the calibration step on data that's different from the training data, and to make sure that calibration is something that's appropriate for your machine learning scenario in the first place. So that's my summary of model calibration, what it is, why it's important, and how to implement it in scikit-learn. As I said, it's an incredibly important aspect of probabilistic models, and it's not something that you can take for granted for out-of-the-box machine learning models. You can't assume that they're well calibrated. So I recommend using calibration reliability plots to get an initial estimate for how well your models are calibrated, and to apply the methods I described in this talk to potentially increase the accuracy of the probability estimates that come out of your machine learning models. Another family of supervised learning models that's related to linear classification models is the naive Bayes family of classifiers, which are based on simple probabilistic models of how the data in each class might have been generated. Naive Bayes classifiers are called naive because, informally, they make the simplifying assumption that each feature of an instance is independent of all the others, given the class. In practice, of course, this is not often the case. Features often are somewhat correlated. For example, in predicting whether a house is likely to sell above the owner's asking price, some features, such as the area of the interior rooms, are likely to be correlated with other features, such as the size of the land that the house is built on or the number of bedrooms. And these features, in turn, might be correlated with the location of the property, and so on. This naive simplifying assumption means, on the one hand, that learning a naive Bayes classifier is very fast because only simple per-class statistics need to be estimated for each feature, and applied for each feature independently. On the other hand, the penalty for this efficiency is that the generalization performance of naive Bayes classifiers can often be a bit worse than other more sophisticated methods, or even linear models for classification. Even so, especially for high-dimensional data sets, naive Bayes classifiers can achieve performance that's often competitive to other more sophisticated methods like support vector machines for some tasks. There are three flavors of naive Bayes classifier that are available in scikit-learn. The Bernoulli naive Bayes model uses a set of binary occurrence features. When classifying text documents, for example, the Bernoulli naive Bayes model is quite handy because we can represent the presence or absence of a given word in the text with a binary feature. Of course, this doesn't take into account how often the word occurs in the text. So the multinomial naive Bayes model uses a set of count-based features, each of which does account for how many times a particular feature, such as a word, is observed in a training example like a document. In this lecture, we won't have time to cover the Bernoulli or multinomial naive Bayes models. However, those models are particularly well suited to textual data, where each feature corresponds to an observation for a particular word. And so you'll see naive Bayes again, including the Bernoulli and multinomial models, in more depth in the text mining part of this specialization. This lecture will focus on Gaussian naive Bayes classifiers, which assume features that are continuous or real-valued. During training, the Gaussian naive Bayes classifier estimates, for each feature, the mean and the standard deviation of the feature value for each class. For prediction, the classifier compares the features of the example data point to be predicted with the feature statistics for each class, and selects the class that best matches the data point. More specifically, the Gaussian naive Bayes classifier assumes that the data for each class was generated by a simple class-specific Gaussian distribution. Predicting the class of a new data point corresponds mathematically to estimating the probability that each class's Gaussian distribution was most likely to have generated the data point. The classifier then picks the class that has highest probability. Without going into the mathematics involved, it can be shown that the decision boundary between classes in the two-class Gaussian naive Bayes classifier in general is a parabolic curve between the classes. And in the special case, where the variance of each feature is the same for both classes, the decision boundary will be linear. Here's what that looks like typically on a simple binary classification dataset. The gray ellipses give an idea of the shape of the Gaussian distribution for each class, as if we were looking down from above. You can see the centers of the Gaussians correspond to the mean value of each feature for each class. More specifically, the gray ellipses show the contour line of the Gaussian distribution for each class that corresponds to about 2 standard deviations from the mean. The line between the yellow and gray background areas represents the decision boundary, and we can see that this is indeed parabolic. To use the Gaussian naive Bayes classifier in Python, we just instantiate an instance of the Gaussian NB class and call the fit method on the training data, just as we would with any other classifier. It's worth noting that the naive Bayes models are among a few classifiers in scikit-learn that support a method called partial fit, which can be used instead of fit to train the classifier incrementally in case you're working with a huge data set that doesn't fit into memory. More details on that are available in the scikit-learn documentation for naive Bayes. For the Gaussian NB class, there are no special parameters to control the model's complexity. Looking at one example in the notebook from our synthetic 2-class dataset, we can see that in fact the Gaussian naive Bayes classifier achieves quite good performance on this simple classification example. When the classes are no longer as easily separable as with this second, more difficult binary example here, like linear models, naive Bayes does not perform as well. On a real-world example using the breast cancer dataset, the Gaussian naive Bayes classifier also does quite well, being quite competitive with other methods such as support vector classifiers. Typically, Gaussian naive Bayes is used for high-dimensional data, when each data instance has hundreds, thousands, or maybe even more features. And likewise, the Bernoulli and multinomial flavors of naive Bayes are used for text classification, where there are a very large number of distinct words as features and where the feature vectors are sparse because any given document uses only a small fraction of the overall vocabulary. There's more in-depth material on the Bernoulli and multinomial naive Bayes classifiers in the text mining portion of this specialization. It can be shown that naive Bayes classifiers are related mathematically to linear models, and so many of the pros and cons of linear models also apply to naive Bayes. On the positive side, naive Bayes classifiers are fast to train and use for prediction, and thus are well suited to high-dimensional data, including text, and to applications involving very large data sets where efficiency is critical and computational costs rule out other classification approaches. On the negative side, when the conditional independent assumption about features doesn't hold, in other words, for a given class there's significant covariance among features, as is the case with many real-world data sets, other more sophisticated classification methods that can account for these dependencies are likely to outperform naive Bayes. And on a side note, when getting confidence or probability estimates associated with predictions, naive Bayes classifiers produce unreliable estimates typically. Still, naive Bayes classifiers can perform very competitively on some tasks and are also often very useful as baseline models against which more sophisticated models can be compared. A widely used and effective method in machine learning involves creating learning models known as ensembles. An ensemble takes multiple individual learning models and combines them to produce an aggregate model that is more powerful than any of its individual learning models alone. Why are ensembles effective? Well, one reason is that if we have different learning models, although each of them might perform well individually, they'll tend to make different kinds of mistakes on a dataset. And typically this happens because each individual model might overfit to a different part of the data. By combining different individual models into an ensemble, we can average out their individual mistakes to reduce the risk of overfitting, while maintaining strong prediction performance. Random forests are an example of the ensemble idea applied to decision trees. Random forests are widely used in practice and achieve very good results on a wide variety of problems. They can be used as classifiers via the scikit-learn random forest classifier class, or for regression using the random forest regressor class, both in the sklearn ensemble module. As we saw earlier, one disadvantage of using a single decision tree was that decision trees tend to be prone to overfitting the training data. As its name would suggest, a random forest creates lots of individual decision trees on a training set, often on the order of tens or hundreds of trees. The idea is that each of the individual trees in a random forest should do reasonably well at predicting the target values in the training set, but should also be constructed to be different in some way from the other trees in the forest. Again, as the name would suggest, this difference is accomplished by introducing random variation into the process of building each decision tree. This random variation during tree building happens in two ways. First, the data used to build each tree is selected randomly. And second, the features chosen in each split test are also randomly selected. To create a random forest model, you first decide on how many trees to build. This is set using the n-estimator parameter for both random forest classifier and random forest regressor. Each tree will be built from a different random sample of the data called a bootstrap sample. Bootstrap samples are commonly used in statistics and machine learning. If your training set has n instances or samples in total, a bootstrap sample of size n is created by just repeatedly picking one of the n dataset rows at random with replacement. That is, allowing for the possibility of picking the same row again at each selection. You repeat this random selection process n times. The resulting bootstrap sample has n rows, just like the original training set, but with possibly some rows from the original dataset missing and others occurring multiple times, just due to the nature of the random selection with replacement. When building a decision tree for a random forest, the process is almost the same as for a standard decision tree, but with one important difference. When picking the best split for a node, instead of finding the best split across all possible features, a random subset of features is chosen, and the best split is found within that smaller subset of features. The number of features in this subset that are randomly considered at each stage is controlled by the max features parameter. This randomness in selecting the bootstrap sample to train an individual tree in a forest ensemble, combined with the fact that splitting a node in the tree is restricted to random subsets of the features at each split, virtually guarantees that all of the decision trees in the random forest will be different. The random forest model is quite sensitive to the max features parameter. If max features is set to 1, the random forest is limited to performing a split on the single feature that was selected randomly, instead of being able to take the best split over several variables. This means the trees in the forest will likely be very different from each other, and possibly with many levels, in order to produce a good fit to the data. On the other hand, if max features is high, close to the total number of features that each instance has, the trees in the forest will tend to be similar and probably will require fewer levels to fit the data, using the most informative features. Once a random forest model is trained, it predicts the target value for new instances by first making a prediction for every tree in the random forest. For regression tasks, the overall prediction is then typically the mean of the individual tree predictions. For classification, the overall prediction is based on a weighted vote. Each tree gives a probability for each possible target class label. Then the probabilities for each class are averaged across all the trees, and the class with the highest probability is the final predicted class. Here's an example of learning a random forest on the example fruit data set using two features, height and width. Here we're showing the training data plotted in terms of two feature values, with height on the x-axis and width on the y-axis. As usual, there are 4 categories of fruit to be predicted. Because the number of features is restricted to just 2 in this very simple example, the randomness in creating the tree ensemble is coming mostly from the bootstrap sampling of the training data. You can see that the decision boundaries overall have the box-like shape that we associate with decision trees, but with some additional detailed variation to accommodate specific local changes in the training data. Overall, you can get an impression of the increased complexity of this random forest model in capturing both the global and local patterns in the training data compared to the single decision tree model we saw earlier. Let's take a look at the notebook code that created and visualized this random forest on the fruit data set. This code also plots the decision boundaries for the other 5 possible feature pairs. Again, to use the random forest classifier, we import the random forest classifier class from the sklearn ensemble library. After doing the usual train test split and setting up the pie-plot figure for plotting, we iterate through pairs of feature columns in the dataset. For each pair of features, we call the fit method on that subset of the training data X using the labels Y. We then use the utility function plot class regions for classifier that's available in the shared module for this course to visualize the training data and the random forest decision boundaries. Let's apply random forests to a larger dataset with more features. For comparison with other supervised learning methods, we'll use the breast cancer dataset again. We create a new random forest classifier, and since there are about 30 features, we'll set max features to 8 to give a diverse set of trees that also fit the data reasonably well. We can see that random forests with no feature scaling or extensive parameter tuning achieve very good test set performance on this dataset. In fact, it's as good or better than all the other supervised methods we've seen so far, including kernelized support vector machines and neural networks that require more careful tuning. Notice that we did not have to perform scaling or other preprocessing as we did with a number of other supervised learning methods. This is one advantage of using random forests. Also note that we passed in a fixed value for the random state parameter in order to make the results reproducible. If we didn't set the random state parameter, the model would likely be different each time due to the randomized nature of the random forest algorithm. So on the positive side, random forests are widely used because they're very powerful. They give excellent prediction performance on a wide variety of problems, and they don't require careful scaling of the feature data or extensive parameter tuning. And even though building many different trees requires a corresponding increase in computation, building random forests is easily parallelized across multiple CPUs. On the negative side, while random forests do inherit many of the benefits of decision trees, one big difference is that random forest models can be very difficult for people to interpret, making it difficult to see the predictive structure of the features or to know why a particular prediction was made. In addition, random forests are not a good choice for tasks that have very high-dimensional sparse features, like text classification, where linear models can provide efficient training and fast, accurate prediction. So to recap, here are some of the key parameters that you'll need for using random forests. N estimators sets the number of trees to use. The default value for N estimators is 10, and increasing this number for larger data sets is almost certainly a good idea, since ensembles that can average over more trees will reduce overfitting. Just bear in mind that increasing the number of trees in the model will also increase the computational cost of training. You use more time and more memory. So in practice, you'll want to choose the parameters that make best use of the resources available on your system. As we saw earlier, the max features parameter has a strong effect on performance. It has a large influence on how diverse the random trees in the forest are. Typically, the default setting of max features, which for classification is the square root of the total number of features, and for regression is the log base 2 of the total number of features, works quite well in practice, although explicitly adjusting max features may give you some additional performance gain, with smaller values of max features tending to reduce overfitting. The max depth parameter controls the depth of each tree in the ensemble. The default setting for this is none. In other words, the nodes in a tree will continue to be split until all leaves contain the same class or have fewer samples than the minimum sample split parameter value, which is 2 by default. Most systems now have a multi-core processor, and so you can use the njobs parameter to tell the random forest algorithm how many cores to use in parallel to train the model. Generally, you can expect something close to a linear speedup. So, for example, if you have 4 cores, the training will be 4 times as fast as if you just use 1. If you set njobs to -1, it will use all the cores on your system. And setting njobs to a number that's more than the number of cores on your system won't have any additional effect. Finally, given the random nature of random forests, if you want reproducible results, it's especially important to choose a fixed setting for the random state parameter. In the examples we've shown here, we typically set random state to 0, but any fixed number will work just as well. Another tree-based ensemble method that's gained wide use in real-world applications is gradient-boosted decision trees. Like random forests, gradient-boosted trees use an ensemble of multiple trees to create more powerful prediction models for classification and regression. In this lecture, we'll provide a brief overview of gradient-boosted decision trees, along with a discussion of their key parameters that control model complexity. Unlike the random forest method that builds and combines a forest of randomly different trees in parallel, the key idea of gradient-boosted decision trees is that they build a series of trees where each tree is trained so that it attempts to correct the mistakes of the previous tree in the series. Typically, gradient-boosted tree ensembles use lots of shallow trees, known in machine learning as weak learners, built in a non-random way, to create a model that makes fewer and fewer mistakes as more trees are added. Once the model is built, making predictions with gradient-boosted tree models is fast and doesn't use a lot of memory. Like random forests, the number of estimators in a gradient-boosted tree ensemble is an important parameter in controlling model complexity. A new parameter that does not occur with random forest is something called the learning rate. The learning rate controls how the gradient-boosted tree algorithm builds the series of corrective trees. When the learning rate is high, each successive tree puts strong emphasis on correcting the mistakes of its predecessor, and thus may result in a more complex individual tree, and thus overall a more complex model. With smaller settings of the learning rate, there's less emphasis on thoroughly correcting the errors of the previous step, which tends to lead to simpler trees at each step. Here's an example showing how to use gradient-boosted trees in scikit-learn on our sample fruit classification task, plotting the decision regions that result. The code is more or less the same as what we use for random forests, but from the sklearn ensemble module, we import the gradient boosting classifier class. We then create the gradient boosting classifier object and fit it to the training data in the usual way. By default, the learning rate parameter is set to 0.1, the n estimators parameter, giving the number of trees to use, is set to 100, and the max depth is set to 3. As with random forests, you can see the decision boundaries have that box-like shape that's characteristic of decision trees or ensembles of trees. Now let's apply gradient-boosted decision trees to the breast cancer dataset. This code trains two different gradient-boosted classifiers. The first one uses the default settings. We can see that the first result has perfect accuracy on the training set, which indicates the model is likely overfitting. Two ways to learn a less complex gradient-boosted tree model are to reduce the learning rate so that each tree doesn't try as hard to learn a more complex model that fixes the mistakes of its predecessor, and to reduce the max depth parameter for the individual trees in the ensemble. The second classifier example makes these changes in the parameters, and you can see that the training set accuracy does decrease while the test set accuracy increases slightly. Gradient-boosted decision trees are among the best off-the-shelf supervised learning methods available, achieving excellent accuracy with only modest memory and runtime requirements to perform prediction once the model has been trained. Some major commercial applications of machine learning have been based on gradient-boosted decision trees. Like other decision tree-based learning methods, you don't need to apply feature scaling for the algorithm to do well, and the features can be a mix of binary, categorical, and continuous types. Boosted decision trees do have several downsides. So like random forests, ensembles of trees are very difficult for people to interpret compared to individual decision trees. However, this often may not matter for many applications where prediction accuracy is the most important goal. Gradient-boosted methods can require careful tuning of the learning rate and other parameters, and the training process can require a lot of computation. And like the other tree-based learning methods we saw, using gradient-boosted methods for text classification or other scenarios where the feature space has thousands of features with sparse values is usually not a good choice for accuracy and computational cost reasons. The key parameters controlling model complexity for gradient-boosted tree models are n estimators, which sets the number of small decision trees, the weak learners, to use in the ensemble, and the learning rate. Typically, these two parameters are tuned together, since making the learning rate smaller will require more trees to maintain model complexity. Unlike random forests, increasing n estimators can lead to overfitting. So typically, the n estimator setting is chosen to best exploit the speed and memory capabilities of the system during the training, and other parameters like the learning rate are then adjusted, given that fixed n estimator setting. The max depth parameter can also have an effect on model complexity by controlling the depth and hence the complexity of the individual trees. The gradient boosting method assumes that each tree is a weak learner, and so the max depth parameter is usually quite small, on the order of 3 to 5 for most applications. In this part of the course, you'll get an introduction to the basics of neural networks, which are a broad family of algorithms that have formed the basis for the recent resurgence in the computational field called deep learning. Early work on neural networks actually began in the 1950s and 60s, and just recently has experienced a resurgence of interest as deep learning has achieved impressive state-of-the-art results on specific tasks that range from object classification in images to fast, accurate machine translation to gameplay. Here, we'll provide an introduction to the basic concepts and algorithms that are foundation of neural networks and of the much more sophisticated deep learning methods in use today. You'll learn about some basic models called multi-layer perceptrons supported by scikit-learn that can be used for classification and regression. Let's start by briefly reviewing simpler methods we've already seen for regression and classification: linear regression and logistic regression, which we show graphically here. Linear regression predicts a continuous output, y hat, shown as the box on the right, as a function of the sum of the input variables xi, shown in the boxes on the left, each weighted by a corresponding coefficient wi hat, plus an intercept or bias term b hat. We saw how various methods like ordinary least squares, ridge regression, or lasso regression could be used to estimate these model coefficients wi hat and b hat, shown above the arrows in the diagram, from training data. Logistic regression takes this one step further by running the output of the linear function of the input variables xi through an additional nonlinear function, the logistic function, represented by the new box in the middle of the diagram, to produce the output y, which because of the logistic function is now constrained to lie between 0 and 1. We use logistic regression for binary classification since we can interpret y as the probability that a given input data instance belongs to the positive class in a two-class binary classification scenario. Here's an example of a simple neural network for regression called a multi-layer perceptron, which I'll sometimes abbreviate by MLP. These are also known as feed-forward neural networks. MLPs take this idea of computing weighted sums of the input features like we saw in logistic regression, but it takes it a step beyond logistic regression by adding an additional processing step called a hidden layer, represented by this additional set of boxes, H0, H1, and H2 in the diagram. These boxes within the hidden layer are called hidden units, and each hidden unit in the hidden layer computes a nonlinear function of the weighted sums of the input features, resulting in intermediate output values v0, v1, v2. Then the MLP computes a weighted sum of these hidden unit outputs to form the final output value y hat. This nonlinear function that the hidden unit applies is called the activation function. In this example, the activation function is the hyperbolic tangent function, which is related to the logistic function. You can see that the result of adding this additional hidden layer processing step to the prediction model is a formula for y hat that is already more involved than the one for logistic regression. Now predicting y involves computing a different initial weighted sum of the input feature values for each hidden unit, which applies a nonlinear activation function, and then all of these nonlinear outputs are combined using another weighted sum to produce y. In particular, there's one weight between each input and each hidden unit, and one weight between each hidden unit and the output variable. In fact, this addition and combination of nonlinear activation functions allows multi-layer perceptrons to learn more complex functions than is possible with a simple linear or logistic function. This additional expressive power enables neural networks to perform more accurate prediction when the relationship between the input and output is itself complex. Of course, this complexity also means that there are a lot more weights, model coefficients, to estimate in the training phase, which means that both more training data and more computation are typically needed to learn a neural network compared to a linear model. As an aside, there are a number of choices for the activation function in a neural network that gets applied in hidden units. Here, the plot shows the input value coming into the activation function from the previous layer's inputs on the x-axis, and the y-axis shows the resulting output value from the function. This code to plot this example is available in the accompanying notebook. The three main activation functions we'll compare later in this lecture are the hyperbolic tangent, That's the S-shaped function in green. The rectified linear unit function, which I'll abbreviate to ReLU, shown as the piecewise linear function in blue, and the familiar logistic function, which is shown in red. The ReLU activation function is the default activation function for neural networks in scikit-learn. It maps any negative input values to 0. The hyperbolic tangent function, or tanh function, maps large positive input values to outputs very close to 1, and large negative input values to outputs very close to -1. These differences in the activation function can have some effect on the shape of regression prediction plots or classification decision boundaries that neural networks learn. In general, we'll be using either the hyperbolic tangent or the ReLU function as our default activation function, since these perform well for most applications. Let's take a look at how we use neural networks in scikit-learn for classification, using the more complex synthetic binary classification dataset. To use a neural network classifier, you import the MLP classifier class from the sklearn neural network module. This code example shows the classifier being fit to the training data using a single hidden layer with 3 different numbers of hidden units in the layer: 1 unit, 10 units, and 100 units. As with all other classification types we've seen, you can create the classifier object with the appropriate parameters and call the fit method on the training data. Here, the main parameter for a neural network classifier is this parameter, hidden layer sizes. This parameter is a list with one element for each hidden layer that gives the number of hidden units to use for that layer. So here we're passing a list with a single element, meaning we want one hidden layer, using the number in the variable called units. By default, if you don't specify the hidden layer sizes parameter, scikit-learn will create a single hidden layer with 100 hidden units. While a setting of 10 may work well for simple datasets like the one we use as examples here, for really complex datasets, the number of hidden units could be in the thousands. It's also possible, as we'll see shortly, to create an MLP with more than one hidden layer by passing a hidden layer sizes parameter with multiple entries. I want to also note the use of this extra parameter called solver, which specifies the algorithm to use for learning the weights of the network. Here we're using the LBFGS algorithm. We'll discuss the solver parameter setting further at the end of this lecture. Also note that we're passing in a random state parameter when creating the MLP classifier object, like we did for the train test split function, and we happen to set this random state parameter to a fixed value of 0. This is because for neural networks, their weights are initialized randomly, which can affect the model that is learned. Because of this, even without changing the key parameters on the same dataset, the same neural network algorithm might learn 2 different models, depending on the value of the internal random seed that is chosen. So by always setting the same value for the random seed used to initialize the weights, we can ensure the results will always be the same for everyone using these examples. This graphic plots the results of running this code to show how the number of hidden units in a single layer neural network affects the model complexity for classification. With a single hidden unit, the model is mathematically equivalent to logistic regression. We see the classifier returns the familiar simple linear decision boundary between the 2 classes. The training set score is low and the test score is not much better, so this network model is underfitting. With 10 hidden units, we can see that the MLP classifier is able to learn a more complex decision boundary that captures more of the nonlinear, cluster-oriented structure in the data, though the test set accuracy is still low. With 100 hidden units, the decision boundary is even more detailed and achieves much better accuracy on both the training and the test sets. Here's a graphical depiction of a multi-layer perceptron with 2 hidden layers. Adding the second hidden layer further increases the complexity of functions that the neural network can learn from more complex datasets. Taking this complexity further, large architectures of neural networks with many stages of computation are why deep learning methods are called deep, and we'll summarize deep learning in an upcoming lecture for this week. Here's an example in the notebook showing how we create a 2-layer MLP with 10 hidden units in each layer. We just set the hidden layer sizes parameter when creating the MLP classifier to a 2-element list, indicating 10 units in each of the 2 hidden layers. You can see the result of adding the second hidden layer on the classification problem we saw earlier. On the left is the original MLP with one hidden layer of 10 units, and on the right is the same data set using a new MLP with 2 hidden layers of 10 units each. You can see the MLP with 2 hidden layers learned a more complex decision boundary and achieved in this case a much better fit on the training data and slightly better accuracy on the test data. Once we start adding more hidden layers with lots of hidden units, you can see that the number of weights, or model coefficients, to estimate for a neural network can increase rapidly, so that more complex neural networks could have many thousands of weights to estimate. We can control this model complexity just as we did with ridge and lasso regression by adding an L2 regularization penalty on the weights. Remember that L2 regularization penalizes models that have a large sum of squares of all the weight values, with the effect being that the neural network prefers models with more weights shrunk close to 0. The regularization parameter for MLPs is called alpha, like with the linear regression models. And in scikit-learn is set to a small value by default, like 0.0001, that gives a little bit of regularization. This code example shows the effect of changing alpha for a larger MLP with 2 hidden layers of 100 nodes each, from a small value of 0.01 to a larger value of 5.0. For variety here, we're also setting the activation function to use the hyperbolic tangent function. Here's the graphical output of this notebook code. You can see the effect of increasing regularization with increasing alpha. In the left plot, when alpha is small, the decision boundaries are much more complex and variable, and the classifier is overfitting, as we can see from the very high training set score and low test score. On the other hand, the right plot uses the largest value of alpha here, alpha 5.0, and that setting results in much smoother decision boundaries, while still capturing the global structure of the data. And this increased simplicity allows it to generalize much better and not overfit to the training set. And this is evident from the much higher test score in this case. As with other supervised learning models like regularized regression and support vector machines, it can be critical when using neural networks to properly normalize the input features. Let's apply the multi-layer perceptron to the breast cancer dataset, and notice that we first apply the min-max scaler to pre-process the input features. Here, we'll combine a more complex network using 2 hidden layers with 100 hidden units each, with a higher regularization setting of alpha at 5.0, and using the LBFGS solver again. You can see that with this multi-layer perceptron, both the training and test set accuracy are among the highest we've obtained on this dataset. Like many of the other supervised learning methods we've seen, you can also use multi-layer perceptrons for regression, as well as classification. We're including MLP regression here as an example for 2 reasons. First, because MLP regression may be useful for some regression problems on its own, but more generally because some deep learning problems are regression problems, and so, as with classification, using multi-layer perceptrons is a good starting point to learn about the more complex architectures used for regression in deep learning. Here's an example of a simple MLP regression model in our notebook. You use the multi-layer perceptron regressor by importing the MLP regressor class from the sklearn neural network module, and then creating the MLP regressor object. When creating the object here, we're setting the number of hidden layers and units within each hidden layer using the same hidden layer sizes parameter that we used for classification. This example uses 2 hidden layers with 100 hidden nodes each. This notebook code has a loop that cycles through different settings of the activation function parameter and the alpha parameter for L2 regularization. Here we've included regression results that use, in the top row, the hyperbolic tangent activation function, and in the bottom row, the ReLU activation function. You can see the smoothness of the activation function somewhat influences the smoothness of the corresponding regression results. Along the columns, the plots also show the effect of using different alpha settings to increase the amount of L2 regularization from left to right. Again, as with classification, the effect of increasing the amount of L2 regularization by increasing alpha is to constrain the regression to use simpler and simpler models with fewer and fewer large weights. You can see this effect for both activation functions in the top and bottom rows. The regression line on the left has higher variance than the much smoother regularized model on the right. On the positive side, beyond the simple examples we've shown here, neural networks form the basis of advanced learning architectures that capture complex features and give state-of-the-art performance on an increasingly wide variety of difficult learning tasks, from world championship play for the game of Go to detailed and robust recognition of objects in images. However, with this increased power come increased costs. These larger and more complex models typically require significant volumes of data, computation, and training time to learn. In addition, careful preprocessing of the input data is needed to help ensure fast, stable, meaningful solutions to finding the optimal set of weights. In general, neural networks are a good choice when the features are of similar types, for example, all derived from the pixels of an image, and less of a good choice when the features are of very different types. Finally, let's review the key parameters for the multilayer perceptron in scikit-learn that can be used to control model complexity. The main way to control model complexity for the MLP is to control the hidden unit size and structure, using the hidden layer sizes parameter that controls the number of hidden layers and the number of units within each layer. Alpha controls the amount of regularization that helps constrain the complexity of the model by constraining the magnitude of the model weights. Finally, you can experiment with at least 3 different choices for the nonlinear activation function by using the activation parameter. Earlier, we saw the solver parameter for specifying the algorithm that learns the network weights. The solver is the algorithm that actually does the numerical work of finding the optimal weights. And one intuitive way of visualizing this process is that all of the solver algorithms have to do a kind of hill climbing in a very bumpy landscape with lots of local minima, where each local minimum corresponds to a locally optimal set of weights. That is, a choice of weight setting that's better than any nearby choices of weights. So across this whole landscape of very bumpy local minima, some will have higher validation scores on the test data and some will have lower. So depending on the initial random initialization of the weights and the nature of the trajectory in the search path that a solver takes through this bumpy landscape, the solver can end up at different local minima, which can have different validation scores. The default solver, Atom, tends to be both efficient and effective on large data sets with thousands of training examples. For small data sets, like many of the ones we used in these examples, the LBFGS solver tends to be faster and find more effective weights. You can find further details on these more advanced settings in the documentation for scikit-learn. As we discussed in the first week of the course, one of the key challenges in machine learning is finding the right features to use as input to a learning model for a particular problem. This is called feature engineering and can be part art and part science. It can also be the single most important factor in doing well on a learning task. Sometimes, in fact, more often, more important than the choice of the model itself. We'll discuss this further in the last week of the course. Because of the difficulty of feature engineering, there's been a lot of research on what's called feature learning or feature extraction algorithms that can find good features automatically. This brings us to deep learning. At a high level, one of the advantages of deep learning is that it includes a sophisticated automatic feature learning phase as part of its supervised training. Moreover, deep learning is called deep because this feature extraction typically doesn't use just one feature learning step, but a hierarchy of multiple feature learning layers, each feeding into the next. Here's one simplified example of what a deep learning architecture might look like in practice for an image recognition task, in this case, digit recognition. recognizing a handwritten digit from 0 to 9, for example. You can see the automatic feature extraction step made up of a hierarchy of feature layers, each of which is based on a network that does convolution, which can be thought of as a filter for a specific pattern, followed by a subsampling step, also known as pooling, that can detect a translated or rotated version of that feature anywhere in the image, so that features are detected properly for the final classification step, which is implemented as a fully connected network. The subsampling step also has the effect of reducing the computational complexity of the network. Depending on the properties of the object we want to predict, for example, if we care only about the presence of an object in an image compared to its, say, specific location, the subsampling part of the architecture may or may not be included. And this is only one example of a deep learning architecture. The size, structure, and other properties may look very different depending on the specific learning problem. This image from a paper by Honglak Lee and colleagues at the University of Michigan shows an illustration of multi-layer feature learning for face recognition. Here there are 3 groups from left to right, corresponding to first, second, and third stages of feature learning. The matrix at each stage shows a set of image features, with 1 feature per square. Each feature can be thought of as a detector or filter that lights up when that pattern is present in the underlying image. The first layer of their deep learning architecture extracts the most primitive low-level features such as edges and different kinds of blobs. The second layer creates new features from combinations of those first layer features. For faces, this might correspond to key elements that capture shapes of higher level features like noses or eyes. The third layer in turn creates new features from combinations of the second layer features, forming still higher level features that capture typical face types and facial expressions. Finally, all of these features are used as input to the final supervised learning step, namely the face classifier. Here are the feature layers that result from training on different types of objects: cars, elephants, chairs, and a mixture of objects. These kinds of complex features can't be learned from a small number of layers. Advances in both algorithms and computing power allow current deep learning systems to train architectures that can have dozens of layers of nonlinear hierarchical features. It turns out that the human brain does something quite related to this when processing visual information. There are specific neural circuits that first do low-level feature extraction, such as edge detection and finding the frequency of repeated patterns, which are then used to compute more sophisticated features to help estimate things like simple shapes and their orientation, or whether a shape is in the foreground or background, followed by further layers of higher-level visual processing that support more complex tasks such as face recognition and interpreting the motion of multiple moving objects. On the positive side, deep learning systems have achieved impressive gains and have achieved state-of-the-art performance on many difficult tasks. Deep learning's automatic feature extraction mechanisms also reduce the need for human guesswork in finding good features. Finally, with current software, deep learning architectures are quite flexible and can be adapted for different tasks and domains. On the negative side, however, deep learning can require very large training sets and computing power, and that can limit its practicality in some scenarios. The complexity of implementation could be considered as one of the negatives of deep learning, and this is the reason that a number of sophisticated high-level software packages have been developed to assist in the development of deep learning architectures. Also, despite the faces example we saw earlier, which gave clear, easy-to-interpret features in most cases, often the features and weights of typical deep learning systems are not nearly so easy to interpret. That is, it's not clear why or what features led a deep learning system to make a particular prediction. While scikit-learn with the MLP classifier and MLP regressor classes provides a useful environment to learn about and apply simple neural networks, if you're interested in getting a deep understanding of deep learning and the software tools required to use it, we've provided some links to additional resources. Typical deep learning development is done with a multi-layer software stack. Here's one example. The higher level layer provides a high-level programming interface that allows you to specify a deep learning architecture with only a few lines of code. In this example, I've chosen Keras for my top-level programming layer. and I'll show you an actual example of Keras in a minute. The higher level programming layer calls into one or more low-level services for things like defining a computation graph that describes the algorithmic workflow, or manipulating data in the form of vectors, matrices, tensors, and so on. TensorFlow is an example of software that provides these kinds of core machine learning framework services, although TensorFlow has a high-level programming layer as well. The higher-level Keras layer makes use of TensorFlow 2 core services. The bottom layer is a hardware-dependent layer that does the lowest level operations like multiplying matrices in a way that is usually optimized for a specific processor or computing architecture. For example, graphics processing units, or GPUs, are a special kind of processor originally developed for video cards that can do extremely fast matrix operations. This lowest layer can take advantage of this kind of specialized hardware to accelerate the training and running of deep learning models. Let me just explain a few of the acronyms here. So BLAS stands for Basic Linear Algebra Subprograms. These are the de facto standard low-level routines for linear algebra. The BLAS specification is pretty general, but specific implementations are typically highly optimized for speed for a given processor. CUDA stands for Compute Unified Device Architecture, and that's a parallel computing platform and application programming interface that allows software to use certain types of GPUs for general purpose processing. We also have new forms of hardware optimized for machine learning called tensor processing units, or TPUs, that are being deployed. CUDNN is a GPU accelerated library that provides highly tuned implementations of routines arising frequently in deep neural network applications. So working together, these three layers are all tremendously important in producing effective and efficient deep learning applications. TensorFlow, PyTorch, and Keras are currently among the most widely used deep learning frameworks. TensorFlow is an end-to-end open source platform for machine learning. It has a comprehensive, flexible ecosystem of tools, libraries, and community resources. And it supports both high-level programming interfaces and low-level core computational services. PyTorch was developed by Facebook's AI research group and open-sourced on GitHub in 2017. It's used for a variety of sophisticated machine learning applications as well, especially natural language processing. PyTorch has a reputation for simplicity, ease of use, flexibility, efficient memory usage, and dynamic computation graphs. Keras is now part of the TensorFlow ecosystem and provides a simple, flexible, top-level programming interface for developing deep learning models. So being able to develop deep learning frameworks in machine learning has multiple benefits. With deep learning, you can generate and iterate new models very quickly, and you can debug relatively easily, which is of huge importance when building effective machine learning systems. More specifically, with these high-level deep learning frameworks, you get the advantage of simplicity. So with deep learning, there's no need for feature engineering. The representation learning and even the architecture iteration are done automatically. You can build pipelines using only a few different vector or matrix tensor operations. These frameworks allow you to do things that are highly scalable. So thanks to these multiple layers that we just discussed, your code is highly amenable to parallelization on high-performance computing hardware like GPUs or TPUs. And you can train these frameworks by iterating over small batches of data, and that lets you handle data sets of arbitrary size. Deep learning models using these frameworks are also very versatile and reusable. They can be trained on additional data without starting from scratch. So it's easy to thaw an existing model, so to speak, add more training data to update the weights, and then, quote unquote, freeze it again for use on your new task. So you can pre-train a model in one domain, like image classification, and you can adjust its training for a different problem, like video segmentation. So I thought it would be fun to show you a specific example using Keras to define a simple digit recognizer. This example is from François Chollet's book on deep learning with Python. So a Keras script typically has 4 parts. The first part, there are some lines of code that prepare the data. So in this case, we're using the MNIST dataset, and so there's some code here to load the dataset. There's a little bit of reshaping that has to happen to get it ready, put it in the right format for the neural network later on. In the second part, after you prepare the data, you define the model. So here we're going to implement this very simple model where we have an input as a digit. We run it through a dense neural net layer that has 512 units. We follow that with a second layer that has 10 units. And you can see that it's very nice that the Keras program, the definition of this sequential model corresponds. You can see very clearly the correspondence between a line of code that adds a layer to the model and the graphical description of the model over here. So it's very easy to create these models in Keras. You define the type of model you want. You add these layers. So it was 1 line of code to add each layer. And of course, you specify for each layer how many hidden units it has, what activation function to use, and so forth. Once you've defined the layers of the model, you do what's called compiling it, where you specify some important parameters like which optimizer to use, which loss function is to be used, and so forth. So that prepares the code internally for the next step, which is the training step. So that's where you fit the network using the training images with their labels. And here you can specify parameters like how many epochs you want to run, how many training images you want to put in a batch as you're training through multiple cycles and so forth. And then, after the model training step, the final step is to evaluate the model. So Keras has some nice simple ways where you can just call this evaluate method on the network using the test data, and it will provide you the loss over the data as well as evaluation metric like accuracy. So this is a great illustration of just how easy it is to use a high-level framework to build a non-trivial neural network that does something interesting. In data science, the term data leakage, sometimes just referred to as leakage, describes the situation where the data you're using to train a machine learning algorithm happens to include unexpected extra information about the very thing you're trying to predict. Basically, leakage occurs any time that information is introduced about the target label or value during training that would not legitimately be available during actual use. Maybe the simplest example of data leakage would be if we included the true label of a data instance as a feature in the model. The model would learn the equivalent of, if this object is labeled as an apple, predict it's an apple. Another clear example of data leakage that we've seen before is having test data accidentally included in the training data, which leads to overfitting. However, data leakage can happen for many other reasons too, often in ways that are quite subtle and hard to detect. When data leakage does occur, it typically causes results during your model development phase that are too optimistic, followed by the nasty surprise of disappointing results after the prediction model is actually deployed and evaluated on new data. In other words, leakage can cause your system to learn a suboptimal model that does much worse in actual deployment than a model developed in a leak-free setting. So leakage can have dramatic implications in the real world, ranging from the financial cost of making a bad monetary and engineering investment in something that doesn't actually work, to system failures that hurt customers' perception of your system's quality or impact the company's brand. For these reasons, data leakage is one of the most serious and widespread problems in data mining and machine learning, and something that as a machine learning practitioner, you must always be on guard against. So now we'll cover what data leakage is, why it matters, how it can be detected, and how you might avoid it in your applications. As an aside, this term data leakage is also used in the field of data security to mean the unauthorized transfer of information outside of a secure facility like a data center. However, in some ways, this security-based meaning is actually somewhat appropriate for our machine learning setting, given the importance of keeping the information about the prediction securely separated from the training and model development phase. Let's look at some more subtle examples of data leakage problems. One classic case happens when information about the future that would not legitimately be available in actual use is included in the training data. Suppose you're developing a retail website and building a classifier to predict whether the user is likely to stay and view another page or leave the site. If the classifier predicts they're about to leave, the website might pop up something that offers incentives to continue shopping. An example of a feature that contains leaked information would be the user's total session length, or the total number of pages they viewed during their visit to the site. This total is often added as a new column during a post-processing phase of the visit log data, for example. This feature has information about the future, namely how many more visits the user is going to make. That's impossible to know in an actual deployment. A solution is to replace the total session length feature with a page visit in session feature that only knows the total pages visited so far in the session and not how many are remaining. A second example of leakage might involve trying to predict if a customer on a bank's website was likely to open an account. If the user's record contains an account number field, it might normally be empty for users still in the process of exploring the site, but eventually is filled in once the user does open an account. Clearly, the user account field is not a legitimate feature that it should be used in this case, because it may not be available at the time the user is still exploring the site. Another example of future information leaking in the past might be if you were developing a diagnostic test to predict a particular medical condition. The existing patient dataset might contain a binary variable that happens to mark whether or not the patient had surgery for that condition. Obviously, such a variable would be highly predictive of the medical condition. There are many other ways predictive information could leak into this feature set. There might be a certain combination of missing diagnosis codes that was very indicative of the medical condition. But again, these would not be legitimate to use since that information isn't available while a patient's condition is still being studied. Or finally, another example in the same patient dataset might involve the form of the patient ID. The ID might be assigned depending on a particular diagnosis path. In other words, the ID could be different if it's the result of a visit to a specialist, where the initial doctor determined that the medical condition was likely. This last example is a great illustration of the fact that there are many different ways data leakage could occur in a training set, and in fact, it's often the case that more than one leakage problem is present at once. Sometimes fixing one leaking feature can reveal the existence of a second one, for example. As a guide, here are some additional examples of data leakage. We can divide leakage into two main types: leakage in the training data, typically where test data or future data gets mixed into the training data, and leakage in features, where something highly informative about the true label somehow gets included as a feature. One very important cause of data leakage is performing some kind of preprocessing on the entire dataset whose results influence what is seen during training. This can include such scenarios as computing parameters for normalizing and rescaling, or finding minimum and maximum feature values to detect and remove outliers, and using the distribution of a variable across the entire dataset to estimate missing values in the training set or perform feature selection. Another critical need for caution occurs when working with time series data, where records for future events are accidentally used to compute features for a particular prediction. The session length example that we saw was one instance of this, but more subtle effects can occur if there are errors in data gathering or missing value indicators. If a feature relates to collecting at least one record in a time span, the presence of an error may give away information about the future. In other words, that no further observations are to be expected. Leakage in features includes the case where we have a variable like diagnosis ID in a patient record that we remove, but neglect to also remove other variables, known as proxy variables, that contain the same or similar information. The patient ID in the case where the ID number had clues about the nature of the patient's diagnosis due to the admission process was an example of this. In some cases, dataset records are intentionally randomized or certain fields anonymized that contain specific information about a user, such as their name, location, and so on. Depending on the prediction task, undoing this anonymization can reveal user or other sensitive information that is not legitimately available in actual use. Finally, any of the above examples we've discussed here could be present in a third-party dataset that gets joined to the training set as an additional source of features. So always be aware of the features in such external data and their interpretation and origin. So how can you detect and avoid data leakage in your applications? Before building the model, exploratory data analysis can reveal surprises in the data. For example, look for features very highly correlated with the target label or value. An example of this from the medical diagnostic example might be the binary feature that indicated a patient had a particular surgical procedure for the condition. That might be extremely highly correlated with a particular diagnosis. After building the model, look for surprising feature behavior in the fitted model, such as extremely high feature weights or very high information gain associated with a variable. Next, look for overall surprising model performance. If your model evaluation results are substantially higher than the same or similar problems on similar datasets, then look closely at the instances or features that have most influence on the model. One more reliable check for leakage, but also potentially expensive, is to do a limited real-world deployment of the trained model to see if there's a big difference between the estimated performance suggested by the model training and development results and the actual results. This check that the model is generalizing well to new data is useful, but may not give much immediate insight into if or where the leakage is happening, or if any drop in performance is due to other reasons like classical overfitting. Let me give you one example of how feature importance analysis can help identify the presence of data leakage. In this example, we're using the feature underscore importances fitted attribute that's computed when you fit a random forest. The idea is to use feature importance analysis to examine features for suspiciously high importance values. And I'll explain what I mean by suspicious in a minute. So in this example, suppose we have a medical data set that includes various features about the patient, their health, medications, location, and so forth, as well as their patient ID in the system. So we train a classifier to predict that a patient will be diagnosed in the future with a certain disease. This is a medical classification task. We train the classifier and then examine the feature importance values. You would expect that features related to health problems or demographics would have higher feature importance weights in this analysis, and that generic features like patient ID or social security number would not be expected to contain any predictive information about someone's health. But when you look at the feature importance numbers, you can see that while social security number does indeed have low feature importance, the patient ID, on the other hand, is listed as the most informative feature. That's very surprising. So that's worth a much closer look to understand why. This scenario actually has happened in real data sets. In one case, the patient ID contained a sub-ID that indicated whether the patient was added to the system by a general practitioner or by a specialist after the problem being predicted had been identified. So in other words, by knowing that the patient ID, the system gets advance warning that a person had seen a specialist and was thus much more likely to have the disease, thus contributing a form of data leakage to this classification problem. There are practices you can follow to help reduce the chance of data leakage in your application. One important rule is to make sure that you perform any data preparation within each cross-validation fold separately. In other words, if you are scaling or normalizing features, any statistics or parameters that you estimate for this should only be based on the data available in the cross-validation split and not the entire dataset. You should also make sure that you use these same parameters on the corresponding held-out test fold. If you're working with time series data, keep track of the timestamp that's associated with processing a particular data instance, such as a user's click on a web page. And make sure any data used to compute features for this instance does not include records with a later time than the cutoff value. This will help ensure you're not including information from the future in your current feature calculations or training data. If you have enough data, consider splitting off a completely separate test set before you even start working with a new data set, and then evaluating your final model on this test data only as a very last step. The goal here is similar to doing a real-world deployment, to check that your trained model does generalize reasonably well to new data. If there's no significant drop in performance, great, but if there is, leakage may be one contributing factor, along with the usual suspects like classical overfitting. For more real-world examples, analysis, and guidance about preventing data leakage, you can take a look at the optional readings provided in the lesson plan. Unsupervised machine learning involves a wide variety of tasks where, unlike supervised learning, there's no target value to be predicted. Instead, the job of the unsupervised learning algorithm is to take the raw data and capture some interesting structure in it. This is useful for a number of scenarios: to explore and visualize the structure in a complex data set, to do density estimation to predict the probabilities of events, to compress the data, to extract more effective features before applying a supervised learning algorithm, or to discover important structures like clusters of similar objects or unusual or individual outliers in the data. All of these and other unsupervised learning tasks have in common the property that there are no target values, labels, or output to learn from or to be predicted. Instead, we only have the unlabeled samples in the dataset as input. Here's an example of an unsupervised method called clustering. Suppose you're in charge of running a website that allows people to buy products from your company, and the site gets thousands of visits per day. As people access the site by clicking links to products or typing in search terms, their interactions are logged by the web server that creates a large log file. It might be useful for your business to understand who's using your site by grouping users according to their shopping behavior. For example, there might be a group of more expert users who use more advanced features to find something very specific, while another group of non-expert users might just enjoy browsing a broader set of items. By clustering users into groups, you might gain some insight into who your typical customers are and what site features different types of users find important. You could use insights from clustering users to improve the site's features for different groups, or to recommend products to specific groups that would be more likely to buy them. So in this lecture, we'll give a brief survey of unsupervised learning methods, divided into two major categories. First, we'll look at one family of unsupervised methods called transformations, because they essentially just run the original data through some kind of useful process that extracts or computes information of some kind. Then we'll look at the other broad family of unsupervised learning methods, which are the clustering methods, like in our website example, that find groups in the data and assign every point in the dataset to one of the groups. Okay, let's look at some important unsupervised learning methods that transform the input data in useful ways. One method, called density estimation, is used when you have a set of measurements scattered throughout an area and you want to create what you can think of as a smoothed version over the whole area that gives a general estimate for how likely it would be to observe a particular measurement in some area of that space. For example, in a medical application related to diagnosing diabetes, density estimation with one variable might be used to estimate the distribution of a specific test score, the plasma glucose concentration number from a blood test, for people who have a particular form of diabetes. With this density estimate, we can estimate the probability that anyone with that medical condition has a particular glucose score, even if that specific score wasn't seen in the original dataset. We could then compare this to the range of glucose levels for people who do not have that condition, which is shown by the red line here. Often, density estimates are then used in further machine learning stages as part of providing features for classification or regression. The more technical way to say this is that density estimation calculates a continuous probability density over the feature space, given a set of discrete samples in that feature space. With this density estimate, we can estimate how likely any given combination of features is to occur. In scikit-learn, you can use the kernel density class in the sklearn neighbors module to perform one widely used form of density estimation, called kernel density estimation. Kernel density is especially popular for use in creating heat maps with geospatial data, like this one. Another very important family of unsupervised learning methods that fall into the transformation category are known as dimensionality reduction algorithms. As the name suggests, this kind of transform takes your original data set that might contain, say, 200 features, and finds an approximate version of the data set that uses, say, only 10 dimensions. One very common need for dimensionality reduction arises when first exploring a data set, to understand how the samples may be grouped or related to each other, by visualizing it using a two-dimensional scatter plot. One very important form of dimensionality reduction is called principal component analysis, or PCA. Intuitively, what PCA does is take your cloud of original data points and finds a rotation of it so that the dimensions are statistically uncorrelated. PCA then typically drops all but the most informative initial dimensions that capture most of the variation in the original dataset. Here's a simple example of what I mean with a synthetic two-dimensional dataset. Here, if we have two original features that are highly correlated, represented by this cloud of points, PCA will rotate the data so the direction of highest variance, called the first principal component, which is along the long direction of the cloud, becomes the first dimension. It will then find the direction at right angles that maximally captures the remaining variance. This is the second principal component. In two dimensions, there's only one possible such direction at a right angle to the first principal component, but for higher dimensions there would be infinitely many. With more than two dimensions, the process of finding successive principal components at right angles to the previous ones would continue until the desired number of principal components is reached. One result of applying PCA is that we now know the best one-dimensional approximation to the original two-dimensional data. In other words, we can take any data point that used two features before, x and y, and approximate it using just one feature, namely its location when projected onto the first principal component. Here's an example of using scikit-learn to apply PCA to a higher dimensional dataset, the breast cancer dataset. To perform PCA, we import the PCA class from sklearn decomposition. It's important to first transform the dataset so that each feature's range of values has zero mean and unit variance. And we can do this using the fit and transform methods of the standard scalar class, as shown here. We then create the PCA object, specify that we want to retain just the first two principal components to reduce the dimensionality to just two columns, and call the fit method using our normalized data. This will set up PCA so that it learns the right rotation of the dataset. We can then apply this properly prepared PCA object to project all the points in our original input dataset to this new two-dimensional space. Notice here, since we're not doing supervised learning and evaluating a model against a test set, we don't have to split our dataset into training and test sets. You see that if we take the shape of the array that's returned from PCA, it's transformed our original dataset with 30 features into a new array that has just two columns, essentially expressing each original data point in terms of two new features, representing the position of the data point in this new two-dimensional PCA space. We can then create a scatter plot that uses these two new features to see how the data forms clusters. In this example, we've used a dataset that has labels for supervised learning, namely the malignant and benign labels on cancer cells. so that we can see how well PCA serves to find clusters in the data. Here's the result of plotting all the 30-feature data samples using the 2 new features computed with PCA. We can see that the malignant and benign cells do indeed tend to cluster into 2 groups in this space. In fact, we could now apply a linear classifier to this 2-dimensional representation of the original dataset, and we can see that it would likely do fairly well. This illustrates another use of dimensionality reduction methods like PCA to find informative features that could then be used in a later supervised learning stage. We can create a heat map that visualizes the first 2 principal components of the breast cancer dataset to get an idea of what feature groupings each component is associated with. Note that we can get the arrays representing the 2 principal component axes that define the PCA space using the PCA.components_ attribute that's filled in after the PCA fit method is used on the data. We can see that the first principal component is all positive, showing a general correlation between all 30 features. In other words, they tend to vary up and down together. The second principal component has a mixture of positive and negative signs. But in particular, we can see a cluster of negatively signed features that covary together and in the opposite direction of the remaining features. Looking at the names, it makes sense this subset would covary together. We see the pair mean texture and worst texture, and the pair mean radius and worst radius varying together, and so on. PCA gives a good initial tool for exploring a dataset, but may not be able to find more subtle groupings that produce better visualizations for more complex datasets. There's a family of unsupervised algorithms called manifold learning algorithms that are very good at finding low-dimensional structure in high-dimensional data and are very useful for visualizations. One classic example of a low-dimensional subset in a high-dimensional space is this dataset in 3 dimensions, where the points all lie on a 2-dimensional sheet with an interesting shape. This lower dimensional sheet within a higher dimensional space is called a manifold. PCA is not sophisticated enough to find this interesting structure. One widely used manifold learning method is called multidimensional scaling, or MDS. There are many flavors of MDS, but they all have the same general goal: to visualize a high-dimensional dataset and project it onto a lower dimensional space, in most cases a 2-dimensional page, in a way that preserves information about how the points in the original data space are close to each other. In this way, you can find and visualize clustering behavior in your high-dimensional data. Using a technique like MDS in scikit-learn is quite similar to using PCA. Like with PCA, each feature should be normalized so its feature values have 0 mean and unit variance. After importing the MDS class from sklearn manifold and transforming the input data, you create the MDS object, specifying the number of components, typically set to 2 dimensions for visualization. You then fit the object using the transformed data, which will learn the mapping, and then you can apply the MDS mapping to the transformed data. Here's an example of applying MDS to the fruit dataset. And you can see it does a pretty good job of visualizing the fact that the different fruit types do indeed tend to cluster into groups. An especially powerful manifold learning algorithm for visualizing your data is called TSNE. TSNE finds a 2-dimensional representation of your data such that the distances between points in the 2D scatter plot match as closely as possible the distances between the same points in the original high-dimensional dataset. In particular, TSNE gives much more weight to preserving information about distances between points that are neighbors. Here's an example of TSNE applied to the images in the handwritten digits dataset. You can see that this 2-dimensional plot preserves the neighbor relationships between images that are similar in terms of their pixels. For example, the cluster for most of the digit 8 samples is closer to the cluster for the digits 3 and 5. In which handwriting can appear more similar than to, say, the digit 1, whose cluster is much farther away. And here's an example of applying TSNE on the fruit dataset. The code is very similar to applying MDS and essentially just replaces MDS with TSNE. The interesting thing here is that TSNE does a poor job of finding structure in this rather small and simple fruit dataset, which reminds us that we should try at least a few different approaches when visualizing data using manifold learning to see which works best for a particular dataset. TSNE tends to work better on datasets that have more well-defined local structure. In other words, more clearly defined patterns of neighbors. Aside from transformations, the other family of unsupervised learning methods are the clustering methods. The goal of clustering is to find a way to divide up a dataset into groups, called clusters, so that groups of similar data instances are assigned to the same cluster, while very dissimilar objects are assigned to different clusters. If new data points were being added over time, some clustering algorithms could also predict which cluster a new data instance should be assigned to, similar to classification, but without being able to train the clustering model using labeled examples in advance. One of the most widely used clustering algorithms is called k-means clustering. K-means clustering finds k cluster centers in different regions of the feature space that it thinks represent very different groups. You need to specify the value of k ahead of time, which is one of the drawbacks of k-means. For some problems, we may know the number of classes the data should fall into, but for many other tasks, we might not. K-means operates by first randomly picking locations for the k cluster centers. Then it goes back and forth between two steps. In the first step, given the locations of existing cluster centers, it assigns each data point to a cluster center based on its distance from the center. In other words, it assigns each data point to the closest center. Then in the second step, it adjusts the locations of each cluster center. It does this by setting the new cluster center to the mean of the positions of all the data points in that cluster. Somewhat magically, after running this alternating process for a while, coherent clusters do start to form, and the cluster centers and the corresponding cluster assignment for each data point eventually settle down to something stable. Now, one aspect of k-means is that different random starting points for the cluster centers often result in very different clustering solutions. So typically, the k-means algorithm is run in scikit-learn with 10 different random initializations, and the solution occurring the most number of times is chosen. Here's a step-by-step example. We first choose 3 locations in the space randomly to be the cluster centers. Then we assign each data point to the cluster with the nearest center. Now, for each cluster, we compute the mean location of all points in the cluster and use that as the new cluster center for the next iteration. Here's the second iteration of the first and second steps. Eventually, after 20 or 50 or 100 steps, things settle down to converge on one solution, as shown here. K-means clustering is simple to apply in scikit-learn. You import the k-means class from sklearn cluster, create the k-means object, setting the value of k by specifying the n clusters parameter, and then calling the fit method on the dataset to run the algorithm. One distinction should be made here between clustering algorithms that can predict which center new data point should be assigned to, and those that cannot make such predictions. K-means supports the predict method, and so we can call the fit and predict methods separately. Later methods we'll look at, like agglomerative clustering, do not and must perform the fit and predict in a single step, as we'll see. Here's the output from the notebook code showing the results applied to the fruits dataset, where we know the value of k ahead of time. Note that k-means is very sensitive to the range of feature values, so if your data has features with very different ranges, it's important to normalize using min-max scaling, as we did for some supervised learning methods. Because each cluster in k-means clustering is defined entirely by its center point, it can only capture fairly simple types of clusters. K-means clustering tends to work well when the data points form into groups of roughly the same size with simple globular shapes that are well separated. K-means will tend not to do well if the data forms long, irregular clusters, for example. Also, the version of K-means we saw here assumed that the data features were continuous values. However, in some cases we may have categorical features, where taking the mean doesn't make sense. In that case, there are variants of K-means that can use a more general definition of distance, such as the K-medoids algorithm that can work with categorical features. Agglomerative clustering refers to a family of clustering methods that work by doing an iterative bottom-up approach. First, each data point is put into its own cluster of one item. Then, a sequence of clusterings are done, where the most similar two clusters at each stage are merged into a new cluster, and this process is repeated until some stopping condition is met. In scikit-learn, the stopping condition is the number of clusters. Here's a visual example of how agglomerative clustering might proceed on a sample dataset until 3 clusters are reached. In stage 1, each data point is in its own cluster, shown by the circles around the points. At stage 2, the 2 most similar clusters, which at this stage amounts to the finding the closest points, are merged, and this process is continued as denoted by the expanding enclosed regions that denote each cluster. You can choose how the agglomerative clustering algorithm determines the most similar cluster by specifying one of several possible linkage criteria. In scikit-learn, the following 3 linkage criteria are available: Ward, average, and complete. Ward's method chooses to merge the 2 clusters that give the smallest increase in total variance within all clusters. Average linkage merges the 2 clusters that have the smallest average distance between points. Complete linkage, which is also known as maximum linkage, merges the 2 clusters that have the smallest maximum distance between their points. In general, Ward's method works well on most data sets, and that's our usual method of choice. In some cases, if you expect the sizes of the clusters to be very different, for example, that one cluster is much larger than the rest, it's worth trying average and complete linkage criteria as well. To perform agglomerative clustering in scikit-learn, you import the agglomerative clustering class from sklearn_cluster. When initializing the object, you specify the n_clusters parameter that causes the algorithm to stop when it has reached that number of clusters. You call the fitPredict method using the dataset as input, and it returns a set of cluster assignments for the data points, as shown here. One of the nice things about agglomerative clustering is that it automatically arranges the data into a hierarchy as an effect of the algorithm, reflecting the order and cluster distance at which each data point is assigned to successive clusters. This hierarchy can be useful to visualize using what's called a dendrogram, which can be used even with high-dimensional data. Here's the dendrogram corresponding to the Ward's method clustering of the previous dataset example. The data points are at the bottom and are numbered, and the y-axis represents cluster distance, namely the distance that 2 clusters are apart in the data space. The data points form the leaves of the tree at the bottom, and a new node parent in the tree is added as each pair of successive clusters is merged. The height of the node parent along the y-axis captures how far apart the 2 clusters were when they merged, with the branch going up representing the new merged cluster. Note that you can tell how far apart the merged clusters are by the length of each branch in the tree. This property of a dendrogram can help us figure out the right number of clusters. In general, we want clusters that have highly similar items within each cluster, but that are far apart from other clusters. For example, we can see that going from 3 clusters to 2 happens at a fairly high y value, which means the clusters that were merged were a significant distance apart. We might want to avoid choosing 2 clusters and stick with 3 clusters that don't involve forcing a merge for clusters that have very dissimilar items in them. Scikit-learn doesn't provide the ability to plot dendrograms, but SciPy does. SciPy handles clustering a little differently than scikit-learn, but here's an example. We first import the dendrogram and ward functions from the SciPy cluster hierarchy module. The ward function returns an array that specifies the distances spanned during the agglomerative clustering. This ward function returns a linkage array, which can then be passed to the dendrogram function to plot the tree. Typically, making use of this hierarchy is most useful when the underlying data itself follows some kind of hierarchical process so that the tree is easily interpreted. For example, hierarchical clustering is especially useful for genetic and other biological data, where the levels represent stages of mutation or evolution. But there are other data sets where both k-means clustering and agglomerative clustering don't perform well. So we're now going to give an overview of a third clustering method called dbScan. dbScan is an acronym that stands for Density-Based Spatial Clustering of Applications with Noise. One advantage of dbScan is that you don't need to specify the number of clusters in advance. Another advantage is that it works well with datasets that have more complex cluster shapes. It can also find points that are outliers that shouldn't reasonably be assigned to any cluster. dbScan is relatively efficient and can be used for large datasets. The main idea behind dbScan is that clusters represent areas in the data space that are more dense with data points, while being separated by regions that are empty or at least much less densely populated. The two main parameters for dbScan are min samples and EPS. All points that lie in a more dense region are called core samples. For a given data point, if there are min sample other data points that lie within a distance of EPS, that given data point is labeled as a core sample. Then, all core samples that are within a distance of EPS units apart are put into the same cluster. In addition to points being categorized as core samples, points that don't end up belonging to any cluster are considered as noise, while points that are within a distance of EPS units from core points, but not core points themselves, are termed boundary points. Here's an example of dbScan applied to a sample dataset. As with the other clustering methods, dbScan is imported from the sklearn cluster module. And just like with agglomerative clustering, dbScan doesn't make cluster assignments for new data. So we use the fit-predict method to cluster and get the cluster assignments back in one step. One consequence of not having the right settings of EPS and min samples for your particular dataset might be that the cluster memberships returned by dbScan may all be assigned the label -1, which indicates noise. Basically, the EPS setting does implicitly control the number of clusters that are found. With dbScan, if you've scaled your data using standard scaler or min-max scaler to make sure the feature values have comparable ranges, finding an appropriate value for EPS is a bit easier to do. One final note, make sure that when you use the cluster assignments from dbScan, you check for and handle the -1 noise value appropriately, since this negative value might cause problems, for example, if the cluster assignment is used as an index into another array later on. Unlike supervised learning, where we have existing labels or target values to use for evaluating the effectiveness of the learning method, it can be difficult to evaluate unsupervised learning algorithms automatically, since there's typically no ground truth to compare against. In some cases, as in the breast cancer example, we may have existing labels that can be used to evaluate the quality of the clusters by comparing the assignment of a data point to a cluster with the label assigned to the same data point. But there are many cases where labels are not available. In addition, in the case of clustering, for example, there's ambiguity in the sense that there are typically multiple clusterings that could be plausibly assigned to a given data set, and none of them is obviously better than another unless we have some additional criteria, such as performance on a specific application task that does have an objective evaluation, to use as a basis for comparison. For example, in cases where the results of the clustering are used as features for supervised learning, we could use the overall classifier accuracy gain from adding these clustering-based features as a measure of success for the underlying clustering. Another issue with evaluating clustering algorithms is that it can be hard to automatically interpret or label the meaning of the clusters that are found. And this is still a step that requires human expertise to judge. As you've probably gathered by following the variety of topics in this course, the world of machine learning encompasses a broad set of ideas and methods, and the field itself continues to advance rapidly. So the goal of a survey course like this one is to cover the most important basic concepts and visit a few of the more important and interesting areas, and hopefully inspire you enough to continue exploring after you finish the course. I've put together this course so it's not only a source of lectures and assignments, but also a collection of useful readings you can draw on based on my experience in this area that I've chosen for you as good starting points to continue your learning in different aspects of machine learning. By now we've covered quite a bit of ground, starting with an understanding of the general concepts and workflow of applied machine learning, and then getting some exposure to a variety of learning algorithms for important tasks like classification and regression, along with an understanding of the important parameters that control model complexity for these algorithms. You should now have a better understanding of critical problems like overfitting and data leakage, along with an idea for some strategies you can use for detecting and avoiding these problems. We've covered how machine learning algorithms are evaluated and how to tune their parameters to optimize different evaluation criteria that may be appropriate for different tasks. Finally, we've applied these ideas with the help of notebook examples and assignments to gain more experience with a very powerful machine learning library in Python, scikit-learn. I want to say something briefly about an important family of machine learning tasks that we've touched on in this course, but didn't focus on specifically, and that is machine learning that involves text. This includes problems such as email spam detection and classifying web pages by topic. The course following this one in our data science series focuses specifically on text mining and machine learning with text. So if you have a particular interest in diving into the use of natural language processing with machine learning, I encourage you to check it out. Thanks for your interest in this course. I've really enjoyed putting together this tour through the fascinating field of machine learning. I hope this course helped you in some way along whatever path of exploration you might have. And as always, we welcome your feedback on any aspect of this course. Thank you, and all the best in your own future learning.